very good afternoon to one and all. So now we have come on the second session of 11th, the fourth day. And today, now we have with us Mr. Shakti Singh. He is assistant professor in the Thapar University in the electrical engineering department, electrical and instrumentation engineering department. And he is an expert in Homer software. So we have him with us. And I just hand over the session to Dr. Shakti Singh. Sir, you can just continue.
Thank you, ma'am. Thank you very much.
आप वहाँ बोलते समय थोड़ा louder बोलना पड़ेगा because mic is here. Then only it's lit.
Okay. Okay. Good morning, everybody. You can hear? Yes. Okay. The Homer software is. See, the first thing is what exactly Homer is and what we can do with the help of Homer. First thing is. So I will just explain one circuit and suppose we have a load, right? And we want to load demand. Okay. We have some load, right? And we want to fulfill this load demand. We want to meet this demand, meet the demand with the help of some renewable energy sources, right? So first thing is how I choose which renewable energy sources I'm going to use first, right? Suppose we have a 20 kilowatt load per day. Per day, peak load is 20 kilowatt, and kWh we can find out very easily. So suppose I have a load curve like this. This is any load curve we have with respect to time, and this is load demand, right? So the first thing is, suppose I want to meet the total load demand by any renewable sources. The first thing is how I will choose the renewable sources. That will depend upon geographical locations. Suppose I want to install a PV system. First thing, right? Suppose I want to start a PV system, and so the only thing, main thing which I required is capacity of PV system. This is simply I am using solar photovoltaic panels to meet this load demand. So this system is not feasible kind of system because every time you cannot meet the demand. Suppose you have a 24-hour data and you have a solar panel system. So this panel is going to generate according to the solar radiation, right? So what will happen when there is no radiation? First thing. Another thing is, let's say suppose the load is AC load. So again there is one problem. We cannot meet this demand because this is AC and this we are generating DC. So one problem is that. Now the second thing is how much PV, how much capacity of PV I require to meet this demand. My question is how we are going to find out how much capacity, how much kilowatt panel, how much rating panel we are going to install at this area where this load demand is here. So the first thing I required is, a, say let's say I'm using, this is, so this is demand again, and I'm using, let's say this is AC load, right? So first I need a converter. See. This is AC bus, this is DC bus, right? We will generate DC, we will convert it into AC, and we will feed to the load, or we will meet the load requirement. We are going to see total demand we are going to meet by the PV system. Now this system is not reliable. Why? Because there is no backup system, right? So what we are going to do is, in this system, in this hybrid system, so again, suppose I use a battery. Right? I'm using a battery. Now what will happen? When I have excess of electricity, I'm going to store in battery, right? When there is a deficiency in, say, electricity, I'm going to use battery. And the circuit will be like battery is DC. Why I put to and fro arrow, dual arrow, because we can charge and we can discharge. And I put this on a DC bus. So there is no need of converter because these all are generating DC only, right? So now the point is, this battery, when there is deficiency of power, we are going to take power from the battery. And another thing is, when we have excess of power, we are going to charge the battery. So charging and discharging of battery is one concept. Now the point is, how I am going to select the sizes of component. Suppose I have a 20 kilowatt peak load and I have some load curve, any load curve which is that depends upon, say, this is summer, this is say, let's say winter, this is daytime, nighttime, any load graph is available to us. According to that load graph, how much capacity I am going to? That is one big question. So I need to design this system in such a way that all the demand is met, first thing. Second thing is, I require this system to be optimized. Second big thing, the second biggest question, second important question is this system is economical or not? Right. Suppose somebody somebody want to put a wind turbine also in this system. So let's say I am going to put a wind turbine. And this is AC wind turbine or DC wind turbine, that depends upon the availability of the wind turbine. So this is directly we can feed to the load. And excess power is generating from wind turbine, we can convert it into DC, and we have a dual converter, AC to DC and DC to AC, and we can feed to the battery. Suppose you want to put a small hydro system. Right? So here again I am going to put it on AC bus. So again, what will be the capacity of small hydro? Suppose you want to, you have, this is called standalone system. We are not connected to the grid. Right? We are not connected to the grid. Suppose we have excess power and we want to connect it to the grid. Again, if I'm not using any backup, so I can connect grid in a dual mode, right? I can take power from the grid, I can give power to the grid. So how this system works basically? How we design this system? That is all about this Homer software. Next question is this system is optimized? Optimized in terms of cost analysis. And at the end, what we are looking for the cost is, we are looking for the cost of energy. How much is the, say, let's say 5 rupees per kWh, 10 rupees per kWh, 15 rupees kWh, or 1 rupees per kWh. So how we are going to find out the cost analysis. So now, see, if I'm using this system, alone system, I'm not using any wind turbine, I'm not using any grid, I'm not using any small hydro system, I'm just using a simply PV system, right? Simply PV and battery. So first thing I will do in today's class, how to find out the size of these panels, first thing. And second thing, we are going to find out what will be the cost of the system. And also we are going to check reliability of the system. Again, suppose if I introduce a wind turbine in this system, so what will be effect on the system? How cost is affected, first thing, and how the size of wind turbine is selected. So we need basically, and again, the last demo of the day will be if I have all this standalone system and I want to work it into, I want say grid connection also. So how grid connection is going to help you? How the rate of charge from electricity from grid, that sensitive analysis is what we call in Homer system. So let's I put a small hydro and I put a here biomass, small biomass system. I can put so many system fuel cells, like whatever system you are. See, in Punjab we used to have enough plenty of biomass, so we can use biomass system. In your Jammu and Kashmir, let's say you have a very resources for small hydro, you can use. In Gujarat and Rajasthan, we have very good of say PV system, Madhya Pradesh. So that depends upon location to location. In coastal area, there is enough wind is there. So first thing will be how we are going to select the component. So this software tells us what is the capacity of the first thing, what is the capacity of the system. We are going to start to feed the load to meet that load demand first thing, and what will be the cost of analysis. Suppose I choose all the component in a system, and again I want to say make a comparison. If solar is economical, right? Wind is economical, and finally biomass is economical. Suppose I also need say a backup. If I am not using grid, so I can use a DG, right? So DZ will be one say this system is why I am using DZ is diesel generator. Now the reliability of system is increased. There is, let's say there are the times when we increase the size of this PV and all this battery, the cost will obviously goes up. So we need to optimize the system. So this software basically gives us optimization or optimal value of components. What we are going to find out in next 1 hour. How DZ is going to work? First thing, we have provisions in software that I want to, let's say we have a load like this, and I want to use DZ here only. So we have facilities that I want to use DZ here only. Scheduling is what we call it. And here I want to feed this power from battery and let's say, sorry, battery and PV only. So how much electricity is generated, how much resources are available, how we are going to choose a wind turbine, the capacity of the wind turbine, the number of battery, how we are going to say find out this bus size, all this technical data also we can find out with the help of this commerce software. Right? Anecdote, please. Right. So I'm going to design three systems. Basically, one with PV plus battery. Again, I am going to introduce some another technology, wind, and finally with DZ and biomass or any technology you want me to introduce. We will solve some some case study variability, right? Okay. Any doubt, please?
No, sir.
So basically, why we need new models? Because we need to expand the grid, right? And we are looking for alternative options like renewable systems we are using. Solar photovoltaic and wind home system, they are most frequent use, and biomass is another, and say small hydro is also like where we have resources. And another thing which is coming up very say in nowadays, that is in fashion, which is called hybrid power system. Hybrid power system is like we are going to mix more than one kind of resources and we are going to meet the load demand. The advantage of any two, we can say if I mix like PV I am using and I am going to put some wind turbine is there, that system is called hybrid system. And it may be a standalone system, it may be a grid connected system, that depends upon what are the applications of system. So in this system, we can see there are so many hybrid system we can use like wind, PV, biomass, fuel cells, small hydros, batteries, how we are going to optimize the system. So I'm going to optimize this system. I'm going to take one system and we're going. So what exactly Homer is? So Homer is basically a software which is software tool, I rather say it, that is hybrid optimization model for electric renewable. And this was designed by NREL, USA, and nowadays almost more than 1 lakh people are using this software. And this is one best part is that it has a free version. You can download it from a site and you can start working. You can design your own models.
So this is a tool for comparing and evaluating micro power technology options for a wide range of applications, such like suppose village power system. Suppose you have a locality, you have a off-grid location, right? And you have plenty of resources available you, like near to hill station, any hill station, you have a very small village and you want to feed power, you want to meet the load demand, then say how you have plenty of small hydro options available with you, you have plenty of solar radiation available with you, you have plenty of wind resources available with you, so you can design your own system. So this has very flexibility, you can give the load and you can design according to your system. And the only thing which is missing in this Homer software is that we cannot go to the electrical side of the system, like what is P value, what is Q value, what is that is one problem. Here this is basically economical aspect we are looking for. We are looking for only the cost of electricity. Suppose you put a small hydro plant, you put a PV system. So we are not going in the detail of like what will be the PU harmonic analysis, all that power system and power quality issues. We cannot deal with this system. We cannot deal with Homer system. I will tell you this. Suppose I want to this room I have, and I want to feed all the power from solar photovoltaic panel. So what will be the capacity of solar power, solar photovoltaic plant? That only I can tell you. But on the bus, what is going on? What is real power? What is say reactive power? What is say anything we cannot tell you. Only cost analysis we do with this, with the help of this one. This is one drawback of this system. So you can design your standalone application, like suppose in your colleges, suppose you're in home, you want to apply a solar photovoltaic, you want to feed power from any source, you can. Grid connected system, there is a facility of connection also. In grid connection, like we take electricity from grid and we feed excess electricity to the grid. Like there is recently in Punjab, we have a scheme that is called rooftop solar photovoltaic scheme, where we put some capacities sort of photovoltaic panel on our houses, and that is dual metering system is in that system is there. Suppose I am in day I am generating power and I am not at my home, so the power I feed to the grid, right? When I come back, there is no solar radiation, so I can take that power from the grid, or I can take money from the grid. Both options are available. I can give number of unit to in a day to the grid, and again I can take it back from the grid, right? Or either I can take money, I can charge this much is the amount I have given to you, you adjust that part into my bill. So both options are available, unit to unit or money to money. So conventional technology, few conventional technology also is still available, like diesel generator is available in this. So wherever a backup is required, I can use a diesel generator. And all this diesel generator power coefficient, and how much diesel power, how much diesel we are going to use, how much capacity, again we can do that part. New technology, some new technology. I will give you how many technology we have in this software. So who can use it? First thing, everybody can use it. Suppose you want to design your own system, you are free to use it. You are not supposed to take any permission from anyone. This is a free version and you can download it from website and you can start working on Homer software. Where and possibly why do we use Homer system? See, suppose you want to make a standalone system for your own locality, so you can design your own system. What potential it have? Again, the limitation I am saying is that it is not on the power system side. So it has a potential that maybe in future, in coming year, they are enhancing the say quality of this software. Maybe in few years you will got that all power quality issues and all the small parts also you can add. So what can it do? It can design a system that is optimal. First thing, that optimal in terms of cost analysis, optimal in terms of money analysis. How much if I'm going to put this photovoltaic with battery, obviously these things now go back with all this renewable energy system like PV and all. The only factor is which is hindering the use of these technologies basically cost. The cost is still out of reach. Means suppose I want to design this system, the cost of photovoltaic battery and this load and converter, that will come say even more than 10 rupees per kilowatt, something like that. So that is one problem. If I'm going to use wind, obviously cost will be down. So that depend upon the. So how does it work? I'm going to tell you, and how to use it. We have a long session for. Now, what are the questions Homer can answer? Should I buy a wind turbine, PV array, or both? Suppose I want to feed this, I want to meet this load demand. I want to install a system in my home where I have a load. So PV will be economical, or wind will be economical, or both will be economical. This is we are going to do with the help of, right? Why I am saying like that? Wind is economical and PV. Let's say you don't have plenty of wind resources available at your location. You have very poor wind speed. Then wind will be mostly say in terms of it will be costly, because to operate a turbine we need a fixed amount of wind speed. And suppose you are going to put that wind turbine in this room, then this is totally wastage of money. So will my design meet growing demand? Whatever demand I have, say I have to meet total demand by renewable sources. And there will be some times in standalone system, the drawback I must say that we cannot meet all demand. Sometime it happens, because suppose I put a 5 kilowatt panel somewhere, so it is going to the output varies with respect to time. So what will happen if I want to meet all the demand? I need to have a storage system. Suppose sometime there is not continuously there is no sun for 10 days, let's say one example. So that means I need to have a capacity bank of 10 days if I'm using the standalone system. But once you have designed the system, we design the system according to the whole year data, but we have never predicted that there will be no 10 days sun. What we do is most of the time we see the previous data. Suppose I want to put a solar photovoltaic panel at NITTTR Chandigarh. So what I'm going to see is I'm going to track, I'm going to see the past solar radiation pattern or solar wind resource pattern from the past years. I cannot predict the future. Let's say 10 days there is no sun. In that case, I need a large battery bank. But I have calculated the battery bank according to the previous data, right? So that is one question. So capacity shortage will be one critical issue, and there will be some time when you, let's say you have a less load and your battery is full and you have plenty of energy with you. Then what you are going to do with that energy, right? So in that case we can have a deferrable load also, that let's I want to pump the water from the ground, and it is not required at a particular time. Whenever I have access of electricity, I'm using it. Suppose I want to use it as a heat energy or thermal energy, whatever. But that if you have enough, we can use. If you don't have enough, we cannot use. So deferrable load will be also there in this system. And in that case, suppose you don't have a deferrable load, then the power will be wastage. Your battery is full, your demand is met, power is wastage. In that case, you have excess electricity. So what you are going to do with that excess electricity? Because at the end, the cost of electricity will be the money spent divided by say the only two factors: the money you spend and the energy you generate. But if you are generating excess energy, we are not paying for it. We will pay according to the load only, because our load demand is like how much kWh per day is the demand. I'm going to give you the bill according to the demand only. If you are generating so much of excess electricity, I'm not going to pay you. That is one problem. Suppose you have designed a system and solar radiation, yeah, any parameter changes. So what will happen? Suppose I put a DC in this system, and all of a sudden tomorrow, right, the price of diesel change. Like every day we have a news in evening that diesel is cut down by 2 rupees, or petrol is cut down by 1 rupees, or they are costly by 1 rupees, 2 rupees, something like that. So obviously my cost of electricity is going to be affected, right? So how much is going to be affected? So we have a sensitivity analysis in that system. If price is this 1 rupees, price is 2 rupees, what will be the cost? So I will design that system according to the sensitivity analysis also. If price change, if solar radiation change, if wind average change, so many parameters, if cost change, so I can feed so many parameters to this. So what is the price of, at the end, Homer will tell us, this is the capacity we are supposed to install, first thing, and this is the price of electricity that you have generated from this system, right? How should I operate my system? Again, I can tell to the Homer, like I have given you one example. I want to feed this complete load by renewable only. I don't want to use DG. So I'm going to put all power from PV generation. Yeah, next thing is, suppose I have a diesel generator and I want to use it in daytime, right? And I have a solar photovoltaic system and I want to use diesel in day due to pollution and any effect, say noise pollution, whatever it may be. So what at that time we have excess electricity, we are going to store it, and when DC is not available, solar photovoltaic not available, we are going to take it back from the batteries, right? So I can fix the schedule also. Suppose 2 hour in like weekdays we have a high load, right? So what will happen in that case? If you are going to fix one system, other system is flexible to you. If you are going to fix one system, rest of the demand you have to feed by the other system. That is one part, right? So how should I operate my system? That will up to me. There are few changes I can make in the system. So what basically Homer do is it estimate the cost and determine the feasibility of system design over the 8760 hour in a year. So what we are going to do in this software, in this Homer, in system, we are going to take 1 year data, complete data, like resources data, like load demand, and we are going to find out number of units, and we are going to find out also what will be the cost of electricity that is available for us. So basically it optimizes the system. It simulate each system configuration. There are so many number of say combinations that will coming out from this system. Let's say this system. There I can see that there are three systems in this standalone system. One is I can meet this demand by PV plus battery. Size will be different. Agree. Second option is PV plus diesel is one option. If I'm not going to use batteries, second choice, right? Third choice will be PV plus diesel plus battery, and fourth choice will be diesel plus battery, right? So these are the four options I have. And sometime suppose I am using DG only, so I don't need a converter that is connected to the AC bus only. So DG obviously cost will be more. If I'm meeting the all load electricity demand from DG only, the cost factor will be one issue. I'm going to use DG plus battery, again I can use it. DG plus battery plus PV, again I can use it. So many options I can. So it simulates all the options to you, and it it rank them according to the cost of electricity. Suppose in this system, PV plus DG only is a better choice. We don't need a large battery backup. Whenever PV is not there, I'm going to operate diesel system. So it may be that it is a economical system. DC plus battery, it may be one of the economical options. So it simulates all say possible combinations, and according to the cost of combination, it finally give you the results that this is the best system. Now it's up to me that I'm looking for the more say economical option, or I'm looking for the more reliable option. It is not going to tell us that this is a reliable system, right? Suppose PV system plus battery plus DG is most reliable system in this case, right? And I'm not supposed to even design it. If I have a 20 kilowatt of peak load, so I'm going to put just a generator of 20 kilowatt. That is one solution, right? Then if I have a PV 10 kilowatt in a day, so I can reduce the size of DG, right? So this is what we are going to find out, size and all that part. And so it configure every possible combination, and it tell us that this is the feasible solution and this is most economical solution. Now it's up to us which solution we opt, right? It sorted all this optimization system by net present cost. That net present cost means cost of electricity. Somewhere it is related. Net present cost of the system and cost of electricity that will come out from the total system. A sensitive analysis like perform an optimization for each sensitivity variable. That let's say I have given you one example. Suppose tomorrow the fuel cost is changed. So obviously that comes under the sensitivity analysis. So next day my cost of now the beauty of this software is you just feed the sensitive analysis and something happen in future. So you know that if price changes, my cost of electricity tomorrow will be 5 rupees per unit or 5.1 rupees per unit. You're not supposed to adjust the thing every time. You just feed the values and you will get all the sensitive analysis. So this is again already I told you that this is designed by NRL, and this is from last 20 years. This is commercially available, and in up to 2009 it has 1 lakh users, and it has been downloaded more than 2-3 lakhs time from that site, and it is freely available. You can and this is one of the best, or you can say what's leading microgrid modeling software. You can design your own microgrid system. It uses both conventional and renewable energy technique. In conventional, it has some limitations. It uses most of the time diesels only, and battery is also conventional. It is intended to evaluate design option for both off-grid and grid-connected power system for remote, standalone, and distributed generation application. Previously, there was no option for grid connectivity and also grid extension. In like 2007 or 8, when I was using it, there was no chance for, if suppose I want to connect this system to grid, there was no like that. In 2009-8, they introduced this concept. Suppose I have excess power, I'm going to feed it to the grid, and grid connection mode is, you know what grid connection mode is. So this you can first thing is how to download it. You can download it from two websites. One is that is NRL, that is from USA, National Renewable Energy Laboratory. You can download it from their website, or we have a separately website for Homer, that is www.homerenergy.com. You can download any of the options. One is that is free, that is Homer Beta or Homer Legacy is the name for routine software, and nowadays they have Homer Pro, which is advanced version of what you say Homer, and it is, but the problem with this advanced version, that is it is only for a trial version. That is that gave you a free 1 month trial, And again, suppose you want to extend, there is no provision. You have to buy that software. But in case of Homer Beta, there is not such a thing. After every 3 months, you have to just update your software and just you need to fill a survey form, and that is totally free of cost. But Homer Pro is not free of cost. That is available for only 1 month, and only a slight differences are there between Homer Pro and Homer. So you can use Homer. There is no problem. Every 3 months you have to just update your data, and that is totally, you can download student version, you can download. If you want to download professional, you need to pay some dollars. So paid is available throughout, and paid may there is no concept of registering again and again and again downloading. That kind of thing is not available. You can be a lifetime member and so many, but little face is required in dollars. So it's up to you which method you are going to opt. But most of the people, they use Homer Beta legacy version. You can download it freely and you can use. In 3 months you can do a little exercise, and that will be again available to you. You need to get a password, and again you can say. So these are the components where this Homer have: solar photovoltaic panels, wind turbines, runoff river hydropower, right? Generators may a variety of generators is available according to the fuel: diesel, gasoline, biogas, alternative, custom fuels, co-fired. Biomass generator is there nowadays. They introduce biomass generator in this. And again, option is electric utility grid. Connected to the grid is also connected to the grid, or off grid. You can grid extension is also there. Suppose you want you want to install this system at a distance of you want to meet this load demand at a distance of 5 kilometers from grid. So that cost also we can calculate. Okay, how much wires we required, how much transformer, everything we can do that in part. And the latest thing is they introduce in this Homer is micro turbine and fuel cell. Fuel cell is the latest addition in this. Storage, there is two method of storage in Homer. One is battery bank and another is hydrogen tank. Nowadays in Homer Pro you can find that they have put even flywheels also, right? Load, you can give any load day to day, and variability in load also. If you can feed 876 hour load according to your demand. Deferrable load, I already discussed that you have excess of electricity, you can go for say water pumping or heat application. Thermal applications is, there are so many load options when we will come to the actual system. So you can download so many publications and so many resource material from various website also. In last, I remember, in last almost 10 years, there are more than hundreds publication in such good reputed journals like Elsewhere, Taylor Francis, IEEE. They are using Homer only. I will give you the few. I will show you some few applications, few case studies where they have applied Homer and they have calculated the cost analysis. So there is a good say scope for research if you are looking for the publication side also. Some input files also supplied by some particular website. Suppose you want to take a solar resource data for particular site. So NASA is providing you free of cost data. You can download hourly data for wind speed, humidity, temperature, say solar radiation at a particular site. You are just supposed to feed some coordinates and you will got one zip file where you have all 8760 hour data available with you, right? So according to that data, we are going to use Homer software, because every time we need data, previous data, current data we don't have, right? Current data means only I can have today's solar radiation or wind speed data, but tomorrow I cannot predict. So what we do, we find a site where say there is a good amount of resources available. I'm not going to put, say, a small hydropower plant in Punjab at Patiala or Chandigarh because we don't have enough renewable options available. So you can go in Kashmir and you can go to Himachal, Uttarakhand, where you can put small hydro data. So every data is available freely at various websites. You can Google it and you can find out. Some meteorological sites are there. Even in your phone, you can find out what is exactly temperature this time, what is humidity this time, what is solar radiation at this time, what is wind speed at this time. You can find out so many data from website. So this Homer is going to tell us what will be the size of PV array. Obviously, we discussed how much is the kilowatt size we required, the number of wind turbines if we are using some say hybrid system, the presence of hydro system. Again, I'm going to find out the size of hydro system, small hydro system. Suppose see what we are. Suppose I have a 100 kilowatt load, and I want to feed it. I want to meet the all demand by small hydro system, right? So what will be the capacity required? It's not like 100 to 100. The efficiency of the system obviously will. Suppose I have a 1 kilowatt solar photovoltaic panel. So at standard condition, the rating value is 1 kilowatt. But if solar radiation is like half of the full solar radiation, so it's going to generate half, right? So that depends upon how much resources we have. Suppose you don't have plenty of water available for small hydro plant, then what you are going to use? We are going to use backup system, and we are going to see reserve, what you call in power system. We are going to have some capacity reserve. Suppose I have a load of 20 kilowatt and I have a DC of say 30 kilowatt. I am keeping it this 10 reserve. So that depend upon what kind of system you want to. Size of each generator, diesel generator. So number of batteries, how much battery we required, and life of battery, and see so many factors will be there. Suppose you design a system for 20 years, let's say. The lifetime of system is 20 years, right? So what will happen is solar photovoltaic panel, they have a life of 20 years. Agree? What about the battery life?
3 to 4 years.
3 to 4 years. So how we are going to accommodate that part, that every 4 year or 5 year we are going to replace the battery. So obviously that will make that will need some money. And once you design a system for 20 years, you have to tell us that these are the replacements I required in 20 years. Let's say you are saying that a battery life is 4 years. Let's say. So how many replacement have we required? At least five request replacement. And again, that five replacement, the problem is that if I purchase a battery of one battery today at the cost of 10,000 rupees, let's say, right? After 5 year, I'm going to replace it. Let's say 4 year or 5 year is the battery life. So at the end means after 4 year, what will be the cost of the battery?
It will be higher.
Yes, it will be higher. So I'm going to include that higher part into my calculation today, right? So I'm going to use that current value of money and past value of money and present value of future value of the money in my system. Suppose I buy a battery today at a cost of 10,000 rupees. At the end of the project life, what will be the value of 10,000? Right? So I have to take all money back from the customer only. I will include the interest also. If I'm investing 1 lakh rupees in a system and I'm doing it for 20 years, so what I will charge the interest? Obviously, I will charge the interest if I'm investing 1 lakh rupees, and after that I'm going to calculate the cost of energy. And in the meantime, suppose 5 replacement is required, so I'm going to calculate that value. After today's battery cost is 10,000, and after 4 year battery cost will be, let's say, 15,000. And what will be the value of 15,000 in terms of today? What I'm going to recover, that I'm going to recover all it from the customer only. I will say 5 rupees is the cost. 5 rupees, like for an example, you have a hydro plant, you have fuel input free. So what is the current money charging? The only you are supposed to give salary to the workers, and your maintenance cost, yes. But why the cost of electricity is too high? Because we have included that infrastructure and capital cost in that. Yes. That's why it's too high. Otherwise, so it should be free almost. Nowadays, it should be free. If we don't consider the capital cost, we are not paying for any input. Yes, only maintenance and few people working on this. It is almost free, but it is not free because we have invested so much amount, and we are taking interest with interest back from the customer. Right. So, what will be the size? Obviously, AC to DC and DC to AC. It depends upon system. Suppose I'm going to use this DC load, right? My load is DC, so converter is not required. If I'm not using DC, I'm using DC load, so converter is not required. So what I have said is converter money. Size of converter I have saved, money in terms of converter I have saved. So that depend upon the system. Suppose I have all AC system, all AC generation. I have a DC and I have a wind turbine. So I don't require a DC bus. I don't have battery. I don't require a DC bus. So it depends upon what kind of application you are looking for. So the dispatch strategy means how we are going to meet the load demand. What is our priority? Our priority is to fulfill all the demand, or it may be sometime that I have a 20 kilowatt say demand, and sometime 1 kilowatt remain say attended. So it's up to me. But I want that every time 20 kilowatt should be met first. My priority is. So in that case, I need to go for the upper side. Upper side means ratings will be obviously high, right? But still, we have say few drawbacks of Homer. One is that this is totally black. This is one drawback with all software systems. That is, they are all black box approaches. Black box approaches means we don't know what exactly is happening inside the system. How they are going to calculate the value. We just feed the data. We say run, right, and it gives us the optimized value. But how it has optimized the system? What technique they have used to optimize this? So it's a conventional, it's a artificial evolutionary algorithm, it's a say some another programming is there. They don't tell us. And sometimes it happens that see the advantage of these software tools, disadvantage of this software tool is that our conventional method. Suppose I do a mathematical modeling of the system, and I find out the optimal size by using any method. Let's say I'm using genetic algorithm, let's say for an example. Sometime it happens, sometime most of the time it happens that these are existing technologies, existing algorithm, they provide you the better result, right? But in that case, you need to say design a mathematical model for that system. You need to calculate according to the solar input. You need to first calculate the PV output. You need to calculate the wind output, wind turbine output according to the wind speed or wind height or wind turbine. Again, you are going to optimize the system. In that case, you need to do physical things. And even in optimization also, we have some optimization tools, right, where we can feed. Again, the concept is there. So, suppose we have a genetic algorithm toolbox. So I'm going to just give the value and that will give us the result. But still we know that this is genetic algorithm tool. But when you are going to apply yourself, you are not using any tool, you are supposed to design a mathematical model. So what we do in research is we take a help of Homer and we find out the optimal sizing of this say hybrid system, and we compare it with the another technology. So there are so many papers available on this that somebody put a Homer and in the same system we put a conventional, non-conventional. Non-conventional means evolutionary algorithm are coming up. So many genetic, PSO, ABC, artificial B colon, C, ant colony, harmony search. So many algorithm are nowadays available with you. So we can apply that also. And if you found better result than this, we can compare that this conventional technique or non-conventional technique is better. But it's still base we take as a homework also. Or if you want to compare between the technology, also that part we can do. Suppose PSO gives some different result and genetic algorithm gives some different results. So there will be some. This is the law. This is not the final answer for the optimization system. There is no limit at all. All the day, say every day, some new technology is coming up, and they say these results are better than the previous technology. Some changes they are doing in algorithm, so they are saying this is a good algorithm. So again, single function minimization is one problem. You cannot minimize multi optimization problem. We cannot solve with the homework. Like you want to minimize the cost, and also you want to minimize the. Suppose I am using this diesel generator concept, right? So obviously diesel generator have some pollutant emissions, CO2 and all that part, right? So we can do only one optimization. Suppose I want to minimize diesel use. I want to use diesel rarely. When it's the last time means critical situation are there, I am going to use 11th hour, right? So that time I want to use diesel. So dual multi-optimization is not there in this system. Multi-optimization means we cannot minimize cost simultaneously environmental issues, pollutions. So that is one problem. In that case, you need to go for the multi-object optimization. Required more computational time as compared to existing optimization technique. This is another factor. When your system grows means the size of system is large. Let's say you put electric two kind of electric load, 10 type of system, battery bank, and 50 times 50 sensitivity analysis, right? And size of the system you want to start from interval of one, like 1 kilowatt, 2 kilowatt, 3 kilowatt, up to 100 kilowatt. System is big, large load is there. Then there is one problem with this system. It takes hours to calculate the value. Even sometime it run all day. You just calculate, run it, and forget it. It will take like 5 or 6 hours, 10 hours. That depends. And for very small application, it do hardly in 2 minutes, 1 minute. But in case of optimization technique, they don't take so much time, right? As compared to Homer, they are very, say, they give very fast response. Genetic algorithm, all these technology, you just model it and just run it on your own PC, say whatever the processor you are having. It takes 1/10, let's say, time of one problem, same problem. So they are very fast. And another issue is that it doesn't consider intra-hour variability. Means we have a time step of 1 hour, like 8760 hour data is there. Suppose now in this 1 hour load is changing, so we don't have that kind of facility available with us. Even in optimization technique, we generally use time step 1 hour. Most of the time in all, say, electrical system, when we talk about load, yeah, load curve, right? Yeah, load demand, whatever. So you have seen most of the time we use 1 hour interval, 24 hour. When we talk about solar radiation, we take a data of 24 hour, and 1 hour is standard time reference. Between the 1 hour, there is 60 minutes, and every minute load or solar radiation can be changed. So that will be a very complex problem. So delta is 1 hour. So how to create, say, uh, how to use Homer is first thing when we'll after the lunch, I'm going to give you the live how we take data, how we feed data, and how we say optimize the system. So these are few slides I just want to show so that next time your software tools, when we are going to use software tools, things will be look familiar to you. So we start a new Homer file like this. This file I am going to show you somewhere. So equipment to consider is first thing. Now it's up to you what model you want to design. First thing, add and remove is one button there. I will show you the screen. First, let me show the screen. This is one say new screen. This is totally blank screen, right? We just downloaded it from NRL website or any website. Now it's free to use, right? So this is the first screen, project one, right? So first thing is, first that thing that come to my mind is uh, for which location I'm going to design a system and what are the sources I'm going to use first. It's up to you. Suppose you have a small hydro available with you. You are going to use it with small hydro. You have fuel cell available with you, fuel cell, and solar available with you, wind, biomass, or generator. So first thing is, and the second thing is, what kind of load we are going to use. Like if we have DC load, system will be this. Sorry, AC load system will be this one. If we have a DC load, we don't need a converter, right? We are not using DC, so we don't need a converter. So same bus pay he same load will be on the same bus, system on the same bus, battery on the same bus. Nothing is required. If we have AC and DC, then things are a little bit complicated because some are generating AC, some are generating DC. So every time we need a converter, and we use a dual converter, AC to DC and DC. And also the rating of converter is also one issue, right? Suppose you have this AC load and you all 20 kilowatt is load, so at least you need a 20 kilowatt converter into efficiency of the converter. Let's say it will be more than let's say 80%, 90%. So size of the converter will be greater than the total demand. Suppose you have DC available with you and you want to feed a 20 kilowatt of AC. So size of converter will be greater than, obviously greater than 22, greater than 20, right? So this is the first screen I'm going to show you, and here I'm going to use add. These are the options available with us. You can see I'm just naming them. Primary load 2, kind of load I can manage. Primary load means, let's say I have two separate units, means one is community load, one is household load, right? One is factory load, one is household load. And in also in load also we have so many different kind of load, like weekend load. I'm just taking one load, right? Just load. This is what we got on a screen, primary load, right? So I'm just taking any load. So when you just click on this load, a screen pop up, right? Now it's up to you how much load you want to give it. So I'm just giving you some little say, if you have a word file with you, 8760 hour data with you have with you, you can import that file also in this software.
Word file or Excel file?
Word file.
Word file.
Word file. Right? Let's say you have a particular site and you know the every hour load data. So you can import it from here. Import file. That file you have that is in your computer somewhere. So when you click on it, and you can find out where the, or you want to enter manually. Let's say I'm just giving some load profile tools, right? So at the first hour, I have a 1 kilowatt load, right? Second hour, 2 kilowatt, 3 kilowatt, 4 kilowatt, 5 kilowatt, 5 at the sixth, seventh at 5. All of a sudden, 8 o'clock, it increases, 6 kilowatt. In day, it increases. It goes up increasing 9, 10, 12, and it goes up to peak of 14 kilowatt, right? And again it slow down, let's say on the reducing side. Whatever the data you have with you, you can give it to it. 3, 4, whatever the curve, shape of the curve you can see from, say, this I am doing manually. You can feed your own file also, right? So this is the daily load profile. You can see in first slide. You can analyze it. This is one day this is month January. I've given it weekdays profile, right? Suppose in weekends pay, there is slight variation in load, right? So I can, let's say, the peak hour is not as much as high as in terms of say weekdays, like, right? Whatever the curve is. See, this is, I have given 2 days data to this. One is in January. On weekend days, different load is there, and on weekdays, different load is there. This is like, I'm saying it winter profile. And in summers,
Sir, we have to make two load curves different, or
yes, we can up to so many. You can feed, let's say, 365 load curve you can feed. In Word file, so you will have every
suppose
day.
we are doing for week and for 5 days.
This is general waveform I am giving. I'm not feeding any Word file, right? Like, this is a load profile in January, right? And let's say in June, load is double. Let's say 2, 4, 4, 4, or 45. Let's say the peak load. See, something like that, right? And again in June we have two variations. One is weekdays, another is weekend. So here you can see that I have given it average. Here you can see in average window that average kilowatt is 170 and average kilowatt is 7 in this particular June. Let's say January total. This is one complete year's average, and peak load is 54. So I have given in June, you see 54. Can you see 54? See here at 10 to 11, I have given it 54. So this is my peak load. So I have to design system according to the peak load, because at any moment we have to feed this 54 kilowatt. From where I am going to feed it, that is up to my application. I am going to feed it by solar panel, wind turbine, or something like batteries with the help, some battery, some wind, whatever. That is up to you, how you want to make your system, right? And again, this is all I have given fixed load, right? Suppose you want to make a variation in load. Let's say I say that every day 10% variation is load is in there. Yes. Now it generates a file of 8760 hours, where from previous day it take automatically 10% variation, right? And again I can say, suppose I want to now you have given it load profile, like so many things we do in Excel. Suppose this is the load profile. Suppose you want to use in your Microsoft Word, you want to use this graph. So how you are going to use this graph? I have given you are going to fit into first Word Excel, Microsoft Excel, and then you are going to plot the curve. Suppose you want to say use your this data in your Word file. So there is no need. Here also you can say copy file, this file, copy meta file, right? Directly it copies. See, meta file. Yes, I'm just going to the paint and I'm just going to fit. See, right? So you can use this file. Now you can convert this file into any file. JPG, PNG, whatever required, you can require it. Say any file save as, just go to save as and you can find PNG picture, and you see this figure is what you call is looking more handsome than Excel file. Yes, right? So you can use that part. Even suppose you want to use this data also. So just go to right click. You can save. You can copy bitmap image. You can copy meta file. You want to save it as PNG file. You can save as meta file. Directly you can save it. Right? You can save any name. Suppose you want to export this data to your.
Excuse me, sir.
Yes, sir.
Sorry to interrupt you, sir. The random variability where you mentioned day-to-day variation of 10%,
Yes, sir.
is it taken 10% on the higher side or 5% higher side and 5% lower side? Could you please
Yes,
explain that?
it will be. I will show you the curve also. I will give you the data. You can see yourself also. I will tell you how to see that part. Right?
Okay, okay,
I
okay.
will
Thank you.
I will show you the exactly data for one complete year. Don't worry, sir. Right,
Okay,
sir?
thank you, sir. Sure, thank you.
So point is, suppose I want to see here in also in second figure you can see January, February, March, April, May. I have taken winter profile. Right? In 4 months, I am just going to use like June, July, August, September, October, November. I am going to use let's say summer profile. And day-to-day variation will be there. I will show you how to take out that data. You will see that it varies 10% positive to say every day. How it varies, you can see that part. Suppose you don't want to, you want to stick to your own data. Let's say you have a 876 hour data and you want to say use your own data, and there is no need of variation. So most of the time, what we do is we take our original data. When we have to design a system, we design system according to our own data. Suppose what is the actual kilowatt is available, what is the day-to-day profile that we take from 8760. We will do that part later on. We will see what is exactly data is. You can see from here you can plot the data. See, this window is coming out from plot. Now you can see, sir. See here. This is load data for complete year, right? Variation is there. Load data for complete year. Now you can call this data in your any file. What you have to do is like January data is there, February data is there, March, April, and summer data is there. Now we are going to see how it's going to vary the data. So what I'm going to do is, again, I can save this file in any format, MATLAB. I want to see this data. I want to export this data. So this will be original data. Let's say I'm exporting it on. This is load data, right? So there will be a file that will be, say, generated on my desktop. Load data. See, right? So this is the data for 876 hours. See,
So it's a word file, sir.
this is a word file, right? This is a word file. This is 876 hour 0 data. This is complete data, right? This is 8760 hour data, and that will be depend upon. See, I have given it. I think variability, 10% variabilities. I have given it here. See, this is scale data. 1.163 data is there. Baseline data, load data. 2.36 is there. 3.9, and I have given it the variability. See, 111 6.97. Next is 8 point something. Variability I have given it to. If you are not giving it variability, the data will be fixed to you. Whatever data. You see, you can take this data from your word file, right? Suppose you have a 876 hours data in your word file. You want to design your own system. No variability is there. See, this is variable. I have given it variability. If I'm not giving it any variability, it will be fixed. See, All data will be fixed. See, I have to run first it. Okay. Okay. Two profile I have given, I think. Yes. What we did is, see, now there is no load variability. The load demand on very first January is same. On 2nd January, yes. Third, again same. Fourth, again same. Fifth, again same. Sixth, it is changed. Why? Yes. Suppose now I want to see on which side it's going to 10%, right? Variabilities I have given. So again I can see it's going to up or down. That depends upon both sides. It can give plus minus. So variability is up to this. So we generally take our own data and we design system according to the data. We normally even don't change the, see, when we increase the number of variables, the time optimization time increase basically. Now we have to design this system according to 4 load graph. One is for winter, weekdays, weekend, right? One is for summers, weekdays, winter. So basically these are 4 problems, and peak load will be same. Peak load will be like I have given it say 54 peak. So peak, uh, let's say this peak happen in one day in June. So the problem is with this system, with this optimization system is that we have to consider that 54 for one day also. And according to that, if we want to meet that all demand, 54, and let's say the variation in load is one day the load demand is 54, and routine or what average demand is 7 only. Now see the difference. We have to design the system according to the 54. And if you're designing system according to the 54, so many say kWh is going to be wastage because we will have excess electricity, right? And here we can scale annual average kilowatt per day. I can change it again. Sensitivity analysis will be there. Suppose I want to see the data for 180, 190 scale average. Scale baseline average is 170. So I can change so many parameters. I can export this file to anywhere. See, suppose now you have any doubt how it calculates thing. First thing is, suppose how we calculate average, how we calculate kilowatt peak load factor, how we calculate, how it day-to-day variation, random variability, it generate, how to all these, any doubt on this screen, suppose you have. So we go to the help side. We just click on the help. See. Now in help side, uh, you will find so many things. Suppose you want to find some data from any particular. Suppose you want to test your system on a standard microgrid. Standard microgrid means suppose you want to see how exactly power is, what is the cost analysis for a standard. We have so many standard test grid data, microgrid data. Like we have a Santa Rita jail in USA that is called to be one of the best microgrid system in the world. And there they have solar panel, wind turbine, and fuel cell system. Totally independent standalone system. So you want to use that load data, and you want to make change in your system. You want to see that load according to that load you are going to put one say, like we have when we talk about power system, we have some standard system like IEEE bus system. But here in microgrid, we don't have such systems. You are the sole owner of your own microgrid. So your microgrid is feasible, reliable, economical. Who's going to tell us? Suppose you want to you have a IEEE bus system and you want to feed some distribution generation in there. So you are going to compare something. But now the problem is, in power system you have existing, established, proven systems. We are going to modify them. But in microgrid, we don't have such kind of system. That is one, say, drawback. And let's say they have data for USA site, and I'm going to deal with the same data here. So there will be variability in data. So that is one problem with the standalone system. Our own system, own data, everything we are on. Solely owner of microgrid system. So my point is, if suppose I design this system, I'm going to verify that part, that this is perfect, or this is okay, or this is reliable. That is one thing. How I'm going to say that this is the load and this is the PV that fits this system best? How I'm going to say that this is the best system? Because this is not a standard system. This is not a IEEE bus system or something like that. This is not a scaled system. So that is one system. So we feed the data, we take it, and so there is no comparison at all. Suppose you pick any case study from any location, for any location from any paper, but you will not get all data. But in case of IEEE bus system, you will got all the data. At this bus, you have this P, you have Q, you have everything, you can get it. But in that case, there is nothing like. So in that case, you design system according to your demand also. And authenticity of the system is that one big issue, that it is okay or not. We can see every time what is power generated. We can see all the data. We can analyze all the data. Like we have a 20 kilowatt load, and I put a, let's say, 50 kilowatt solar panel. So I can see at that this hour this panel is generating this much of amount, and this is the amount stored in battery. This is the electricity stored in battery. This is the wind turbine generating right now. I can see the whole data, right? But authenticity is nothing, because they are not standard data. Standard data, it cannot be. In a microgrid, you cannot have a standard data, because they are designed according to their geographical locations. The same value, the same load, same resources, they are not going to provide us. And we need so much of data for analysis. So that is one. Now you see, finding data to run Homer is, these are the few websites you can find out solar radiation data, monthly solar radiation, wind speed, everything, wind speed data. You can find it out from so many sites. NASA is providing you free of cost, say all data, all 876 hour data, right? So here you can find out. Here you can type what we are looking for. Anything, say solar. Just type any word. How, say, state of charge, whatever you have any query, you just type here and you will load variability I'm looking for. See, load data. See how we calculate load factor. So there is a help in system where you can find out whatever query to you is. See, I've given you the load factor. See here, load factor is 0.131. So how we calculate load factor? See here, if you have an average load of 66 and the peak load is 10.5, the load factor is simply 2.5 divided by 0.26. So these all play a role in load factor. That's what I'm telling you. We have a peak of 54 and we have a average of 7. So load factor will be, say, different. So load factor is going to play a role, right? What other factor was we were looking for? The variability, right? Random variability. So you can find out how it's going to vary the load. This is solar data. Can you find out any word here? Random variability. No. So we can see it from there. how it's going to vary load is variable. We can see it from the data only. 10% what we were talking about. Suppose I am giving it 10%, so I can plot it again. Now see, we can see it for 2 days, and we can find out how it's going to be vary time to time step or 10%. See, now I'm going to just zoom it a little bit. Now you see. Yes. Previously, I have fixed the data. No load variation is I have given to it. So now it's see. Now your answer is it can go up. I think for both in both directions. See 10%. See here, right? It goes down. It goes up. So 10% is on both sides.
Excuse me, sir.
Yes, sir.
So could you show me this the data for these 3 days with 10% and without 10% adjustment?
Okay. But we have given time to time step day. We have given random variability day to day 10%, right?
Now, if you could reduce it to 0 and then compare the two graphs, if that can be done.
Yes, sir. This is the data I got from 3 days. So
Okay.
let's see what it do, what Homer do, right? So this is the scale data 1.66 on very first day, right? Can you see that part? 1.
Yes, I can.
1.166, 2.223. This is scale data 4.4348, and this is 10%. I think. No, this is it is taking. Okay, yes, this is taking. The next data is 0.904. Yes, sir. Can you get it?
Yes, sir, I can hear you.
The first data was 1.166,
Okay.
and next day the data is 0.904.
So what I am asking you is that with the random variable set to 10%, each and every what do you say? Each and every data for each and every time, is it varied by 10%, or is
Yes,
it varied by 5% in the positive side, 5% in the negative side? That is my question, sir.
it is 1 hour data at the C at on January 1st, 1 hour pay data is 1.166, and January 2 pay data is 0.904, right? Right? There is no plus and minus, and in on next say January 3rd, the data is 1.086 of previous day data. See, just note down three values: 1.166, and another value is 0.904, and third value is 1.086. Now you can calculate how it's varying, right?
Okay, okay, sir.
Okay, you can calculate. There will be 10% variation will be there, right?
Okay, so every month for that particular
Not,
date there will
not
be a
every month. Not every month. Every day it's going to vary your load 10%.
okay for every day. Fine.
Yes, it sometime it's up, sometime it's down. Variability means plus or minus both, right?
Okay.
In
Okay.
one
Thank you,
side,
sir.
in one side, so it's going to increasing every time. If I'm going to increase load every day 10%, so load will be increase every time. See, so annual scale down, say average, we have to maintain. So that's why variability is there. But you are not supposed to take it variable data, because we are working on our own system. So we are going to feed this data basically, right? We are going to take a data from any location, any power plant, any where, any distribution center, whatever it may be. So we are going to give personally or a word file to this system. Now you see, January 1, January 2 down, January 3 again down, 4 again. See, all variable is there. See, now you see the graph. And when I'm now, you just see, when I'm not going to give any variability to the load curve will be something like state. I'm not giving it any variability. See, now I'm going to plot it. See, they all are same, right? See here, January 1st, January 2. See, I'm not varying any load. Whatever load I have given to it, it has taken scale data, and everyday load is same. See, January 3rd load is same, January 4th load is same, and we have given it. See, weekend days different load. So January 5 and January 6 load is different, and you see January 7 again we have given the same load, and January 8 see again, right? We have made these changes. We have given it 4 load. One is summer load on weekdays, on weekend days, and winter load on weekdays and winter days. Suppose I want to make it variable. Why I need to make it variable? First thing is, suppose I don't want to show one single graph to you. So let it be do some exercise that variability can be there. And I know that it can goes up to, suppose I have a load curve. So I know my load curve. Chronological data will be there. So I know that this load is going to be very only 10% or 20%, or it can be very 50%. So that in that case, system will be different. Right, so it's up to you how you are going to use that load part, right? So again, you can export this data and you can plot again. Same story is there. You can call this in a Word file. Suppose you want to use in your Excel file somewhere. You want to plot this data. You want to directly. You can use pictures also from here, right? That's up to you. See, you can use both options. You can copy this file and you can say export this data to any Word file. That's up to you, right? So it's all about what kind of system you want to design. Suppose you want to keep load demand constant throughout the year. See how it looks like now. January. Now let's say in June, I just want to use the same load. So every time this curve, June, July, August, they will be the same. I don't want to be my load to be variable. I have a fixed schedule of that this is the load and I want to design a system this year. So you can calculate it. You want to change any sensitivity analysis, you efficiency input, you whatever. See, you want to give it to load factor you want, and see another is DC load. Suppose now when you click to the DC, it becomes a DC load. Now I will design system. DC bus will be different. See, if I'm taking, now you see this is changed. This screen is changed. This is now DC load, right? This is 170 kilowatt hour per day ka load hai. Peak hai 54. No variability is there. Nothing is there. Only I just want to design my system according to this DC load. See, right? So next part is what I want to, how I want to meet this load, what I am going to apply. Suppose I want to, first I will take the example of solar photovoltaic, right? Okay.
I think we can break for lunch if it is next. Then after lunch we can baat shuru kar sakte hain.
Okay.
So now I think we will break for lunch, and afternoon also we have this Homer software. So sharp 2:15 we will reassemble. Okay, so all of you 2:15 the session will start again. So I just want all of you to come back at 2:15. Let us start the session. I think most of the nodal centers they have made their participants get seated. So now let us start with this session on Homer. Okay, sir.
Thank you. Thank you, and welcome back. So so far we have decided that we are going to have a DC system or AC system, right? So we have collected all the data required for the load, right? So this was the load, and let's say I'm just making it simple, and I'm just putting it like peak is not 54. I just want to make it somewhere like where is 54? Huh? Where we have given 54?
Very important.
Where? Okay, let's leave it. So this is the load we have taken, and let's say I have taken DC load, so things will be different, right? Now the second thing is how I am going to what source I am looking for. The first thing is, right. So the first, let's say I'm going to meet this all load demand by solar photovoltaic panels. So I'm going to put one PV, right? So PV is not connected because we are not given any data, not resource, nothing like that. So here, once you just click on this, now you are supposed to give the cost analysis of PV. First thing, like suppose one kilowatt PV cost you all cost will be in dollars only, right? No Indian rupee, no euro, nothing like that. All money value will be in dollars only. Suppose you purchase a 1 kilowatt solar panel for, let's say, $1,000, right? And replacement cost obviously the same. And you want to change the replacement cost, let's say 800, you want to keep it. Operational and maintenance cost, let's say $1 per year, yeah, $5 per year. It's up to you how you manage the cost. Now size to consider is 1 kilowatt. That is up to you how much size you are going to give it to. If we want to put a cap on size, we will find out another source that will be the maximum value of, let's say, that will decide according to the load. Let's say 50 kilowatt is a peak, right? So I'm going to just give it random size number, 2, 3, 4. The more is the number, more is the optimization parameters, right? 6, 7, 10, 15, 20, 25, 30, 35, 40, 45, 50, something like 55, 60, 100, whatever the number I am giving. If you are giving in increasing order, these are the number. This is basically a variable. From all of these given data, he will select the best for you, right? So this is, let's say, 65 and 70 or something like that. Now, again, this is DC, right? So solar photovoltaic is DC. Here you can change every value. Lifetime is, let's say, 20 years, and you think that something is 10 year, so you can change. Even you can change the sensitive analysis. Suppose lifetime is 30 years, so you can give this data 40 years, let's say. So it will simulate for 20 also, and for 40 also different system, for 50 also, whatever the value you give, it will simulate differently, right? Derating factor is one constant, that is something like efficiency of constant for solar photovoltaic panel. I will tell you the formula how we got derating factor. Slope degree, how you are going to put your solar photovoltaic panel, what slope you are going to give it from the horizontal, azimuthal degree, whatever the, see, locations, west, south, ground, say reflectance, whatever values, let's say tracking system. This is advanced system, right? Suppose you want to put a tracking system, so you can adjust power according to the movement of the sun, right? So if you are not giving any, you are not applying any tracking system, it will give you fixed value. No power will be changed. Power will be changed according to the solar radiation only, right? So it has some mathematical equations from where it calculates the thing. Let's say consider effect of temperature. When you calculate solar photovoltaic power, we take consider major two factor is involved. One is temperature outside, one is radiation, solar radiation. So if you want to take effect of temperature, or if you don't want to take effect of temperature, you can remove it from here. And how solar panel calculate power, see, we can go to the help. See, this all help is available here. Derating factor, what is derating factor? You can click and you can find out derating factor. Does Homer account for the effect of temperature? Yes. If you say yes, now the best part is in some book you will find that there are hundreds of equations to calculate the power of solar photovoltaic panel from solar radiation. How Homer calculate power? So Homer calculate power, you can click to this and there is one formula. I will come to this formula later on. This is how solar photovoltaic power is calculated. Here there are four major parameter. One is rated capacity of PV array, YPV, that is its power output under STC condition. Suppose you are taking 1 kilowatt power, it can generate 1 kilowatt maximum, its rated value. In according to, and the rating factor is what we give 80%, let's say wastage in atmospheric conditions or electrical or whatever. 80% is the rating factor. GT is the solar radiation incident on PV array, right? GT-STC standard test condition, that is 1 kilowatt per meter square. So the idea of solar power generation is, if you have 1 kilowatt per meter square solar radiation at a particular solar panel, then it can generate 1 kilowatt panel is there and it can generate 1 kilowatt. And if you have a derating factor of 100%, if derating factor is 80% and you have solar radiation 1 kilowatt per meter square, it can give you 1 kilowatt. We don't consider area in this. 1 kilowatt is radiation is there, we just calculate the power according to the formula. Alpha T is temperature coefficient of power, TC is PV cell temperature, TC-STC is standard test conditions. And finally, if you are not considering any effect of temperature, the very simple formula, very easy formula to calculate power is PPV equals to YPV FPV GT GTSC. So simple formula. GT is solar radiation. Its rating will be kilowatt per meter square. Let's say you have half solar radiation, right? So half, GT is half and GT is 1. The GT bar is half and GT bar STC is 1. And let's say 1 kilowatt panel is there, 1 kilowatt and 80% derating factor is there. So 1 into 0.8 into half divided by 1 is the power generated at any particular site, right? If you are taking effective temperature, we are going to use this formula, the upper one, 1 plus alpha P TC minus TCR TC. So as like solar photovoltaic panel, we are going to find out power, all different powers like wind turbine, thermal, diesel generator power and small hydro power. So we have equations for that. Like in small hydro, we have waterfall, height of the all these parameters. So you can find out from here how small hydro. You just type here small hydro and everything whatever related to C, you will go to everything, right? You can go to help site and you can find out how power is generated. See what is head count, what is say hydro head, every data you can find out it. How effective head, all these data. This is for a small hydro. In case of wind, you can find out right, wind data, right? Wind data, everything is there. Wind speed. So every mathematical equation is available with the help, right? So now, so far what we did is we have put a let's say up to 70 kilowatt panel maximum. This is maximum value of solar photovoltaic panel I am providing to Homer. Let's say system is not feasible, so it will give me some warning that this is not a feasible solution. Please add some more photovoltaic or some battery, something like that, right? So once you have decided the solar photo, now you can add, let's say you want to add some battery. So I can go for battery. And here you can find three main features on this screen. One is do not model grid, right? System is connected to grid, and compare standalone system grid extension. These are three different case studies we can do with this Homer. Do not model grid means this is a standalone system. We are not connected this to the grid. When you click on system is connected to grid, grid window will pop up and you have to feed the data, right? I will show you how grid connected system is going to work. Compare standalone system to grid extension. When we are talking about grid extension, we are going to compare the cost. Standalone is better, or we should extend the grid to that particular location. So any three system we can do. So I'm doing first, do not model grid. I'm not connected this system to the grid. So I'm just say adding the battery. Clear? Now, when I click to the battery, there is again this window come up. Now we have to provide the battery input, right? First thing is, here there are so many inbuilt battery specification in there, right? When you click on any specification, you will find details of that battery. This is the chart of that battery. This is data sheet of that particular battery. Even some website is also given to you. That see, this is a Trojan L16P battery, right? You can find out how much ampere hour is there, how much voltage is there, round trip efficiency is 85%, right? But the problem is that you cannot change anything. This is an inbuilt system, right? Suppose you want to build your own battery, you can start with, like, say, new battery, right? So you can give this data. Let's say you design a battery and that has 100% efficiency, right? So here you can give, you have a battery that is 1360 ampere hour capacity. That is local battery, you can say. But if you have some standard battery, just take the data and just feed it, right? See, so these are the few parameters which you can see. So what basically we need in that case is, again, we are looking for the cost. And now you see this is, I have taken Trojan L16P, right? So this is a battery, 6-volt battery, 360 ampere hour, 2.61 kWh, right? When I multiplied with 6, this is 2.16 kWh. Lifetime throughout is kWh. Now I will decide the battery per string. I will decide the bus voltage side, right? Let's say I take just battery per string, 6 volt ka one battery hai. I'm just taking 20. So bus voltage will be 120 volt. So there will be battery per string 20. So 20 into 2, sorry, 20 into 6, 120 ka bus ho gaya. Bus voltage. Bus voltage is 120. This is the only factor where we talk about the bus voltage. In one string there will be 20 batteries. So if I choose a different battery, let's say that is this one. This is a 2-volt battery, but ampere hour is very high. See, 2500 ampere hour is there. So I will take again now 20 battery. The bus voltage is only 40. Right. So agar if I want to make a bus voltage of 120, 60 battery I need. So it's up to me how much I am going to use. See, I'm just taking it. Now minimum battery life, again, that was a sensitive factor. What is the minimum battery life? 4. Let's say I'm saying 3 to 4. And see, I can go it for like floating battery life also. Floating battery life means what we say is 3 or 4 year is a rough number. Suppose we use it proper, we maintain every condition for the battery. It can go to up to 10 years. There is no problem. जो specifications हैं, if we keep that in limits, the life of battery can be increased. It's not like that every 4 year you have to dump your battery. It's not like that. It may be that its life is 6 years, 7 years sometime, and sometime even less than 4 years. If there is some damage, then it can be go beyond, say, 4 years also. So it's up to you how you choose floating life. It can be 10 years if you maintain the charging rate and discharging rate in level, and you maintain the SOC, state of charge of the battery, within the limit. Let's say I say that battery should never go beyond 30% of its final value. Let's say one example. That means 30% charge it has to be there every time. Suppose you take out total power from the battery. Again, you start from the zero. So the life of the battery will say change in that case. So we have to maintain that limit. And here I have mentioned you the limit. See, details. Minimum state of charge 30%. That means this battery will not go down beyond 30%. maximum it can like 70% it can discharge only, right? And it cannot be charged above 100%. Obviously, that is SOC maximum. And you can even fix SOC maximum also. Let's say you want to charge up to 80%. You don't want to be charged a battery fully. Then you can change the limits, right? So again, I have to give some money value. So let's say one capital cost of the battery. It's up to you from where you purchase and what is the cost. Operating and maintenance, जो भी. Size, how much you want to give, 1 string, 2 string, 3 string, 4 string, 5, 6, 7, 8, 9, 10. This is, that means 10 into 20, we can have maximum 200 batteries, right? Right? Number of batteries we can have 200. And what one battery cost us 1 into 200. Yes, any doubt is there? Okay. So number of battery we can increase. Let's say 12, 14, 15, 18, 20, 25, 300, whatever the maximum. Let's say you want to fix number of battery, right? Let's say I can have maximum 300 batteries. I want to keep battery minimum. So if you want to keep battery minimum, you have to go voltage limit high, plus you have to need more, say PV install capacity will be increased, or you need to put backup. And suppose you want to only PV and battery only, then limit will be there. Let's say I'm just putting it 1000. Let it be decide. Let's say it will give you me the value, final value. You just go and you just put this much of kilowatt of panel, and these are the number of batteries you put.
That means these are the batteries we can afford that we are specifying over here.
Yes, this up to you. Suppose
So that is not final.
no,
That
that's
calculation
see
did not be done.
optimization is what you every time in optimization what we do is we fix a maximum value all the time. Otherwise, so there is no limit,
Okay.
right? Once like you want to optimize two parameter x and y, so you will tell na, where your x and y lies.
Yes, yes.
0 to 100 x lies and y lies 0 to 100. So optimization value will be between 100 and 100. Else you don't fix the values, it will be always minimum to 0,
Yes.
right? If you want to minimize any equation, answer will be x equals to 0, y equals to 0, say minimum value, right? So maximum 100, 100 to 100, what is the optimization value? That is some constraint is there. So let's say you want to give any random value to the batteries, that I can afford any battery. See, number of battery increase, the cost will increase.
Yes.
Both are say contradicted, contradicted. Number of battery increase, cost increase. So we are going to minimize the thing. So and sometimes system is not feasible, so don't worry, it will give you some warning that the system is not feasible. Either you increase the size of battery, either you put a backup, you increase the size of photovoltaic, or reduce the load. It will say something like that. So we have put this, right? And this is AC load and photovoltaic is DC, right? Battery is DC. You can see the both way, two-way around. Battery power can be stored, and now system is not connected. There is one gap is inside the system. The load is not connected to the supply. This is called schematic diagram, what I have already built in on Blackboard. System is not connected. There is no power flow. So what we do is we need a converter, right? Because we are generating DC and we are now you see the interesting part. If I just change this load into DC, everything will be okay. See here. No need of converter. PV is generating DC, battery is storing DC, load is DC. So directly PV to DC, battery to DC, two-way switch is there, two-way connection communication is there with the battery, PV one way, load one way, right? But you see, I cannot model it to the grid. Grid I cannot feed DC, right? So I need a converter. Let's get back to the AC load, right? So what I need is I need a converter, right? Until unless you don't fix up the parameter, it will not be connected. Now see, I have not given anything. So I will take a size of 1, and let's say the cost is 100 per kilowatt again. Operating cost is 1, whatever it may be. Lifetime. Here in at this window, I can put more and more sensitive analysis. Let's say what happen if inverter life is 20 years? What happen if inverter life is 25 years? Right? Suppose 15 years is fixed. What happen if inverter is we have a different inverter that goes up to 20 years? Same value, same.
More possibilities can be.
Yes. Number of more. See, these are number of variables. You are giving more and more variables to the system. So obviously, system will be complicated. And it gives me the result on 15, on 20, and 25. It will give me the 3 different results. On 15, the cost will be this. If lifetime is 20, what will happen? What will be the factor in this case? The cost will change. See why cost will change. If you have a lifetime of solar photovoltaic 20 years, right? And you have a lifetime of inverter converter 15 years. So that means
Inverter needs to be
replaced,
Well,
right? Inverter need to be replaced after 15 years. One more thing. After you have taken life of inverter 15 years, and your project life is like 20 years. So what will happen to the rest of 10 years of inverter? You will get a salvage value also. After 20 years project will be finished. So what you are going to be do with that inverter which has a life of 10 years still remaining within? We are going to resell it. We are going to find out salvage value of money. If I purchase one thing in 10,000, according to salvage concept, I purchase a car in 5 lakh. So its value is, let's say, 10% decreasing every year. So after 10 years, its value will be 10, 10, 10, 10, that kind of year. So salvage value will be there on each and every component, right? Like battery. If I have a project life of 10 year and battery life I have given 4 year. So what will happen to the 2 year? So we are going to resell that part. That is called salvage value of the system. So salvage value and everything that it consider totally. Again, you can go to the help site if you have any problem. You can click on the help button and you can find out what exactly you are looking for, right? Now you see efficiency is 90%. Rectifier input, we are using dual, right? AC to DC and DC to AC, both way. So rectifier efficiency I can give, inverter efficiency I can give. In both way efficiency will be different, or it can be same. It depends upon you how you are taking. When you convert DC into AC, things will be different. AC into DC, let's say efficiency is different. So that's up to you how you take. Again, size accordingly. I just give a random number. I just take the peak load demand and I just give the number. When we model system in grid mode, we have a different concept for inverter size, right? So I'm just giving it some values, 3, 4, whatever the values. I will not take the exactly 4, right? 50, 100. The more of the variables you give size to consider, the more complex becomes system, because it has to find out your answer from these data only, right? So calculation time will increase if you keep the steps like 10, 20, 30, 40, 50, let's say. So it will select from all these 5 sizes, right? And if you give 50 like 1, 2, 3, 4, 5, so it has now 50 variables with this. So it will take more time, but it will do, right? And accuracy will be, in that case, it will be more because it will give you the perfect result, right? but time taken will be more. In that case, you simulate. Now you see this system is connected. This is a complete system now, right? Now the point is we have not provided any resource data to the system. We have taken the load, that is up to us. What is the load, DC, AC? Now we have not feed any resource data. Suppose I put a this system in USA, in India, in China. So how it's going to be work differently. So the thing is, first and interest rate and all these things. So these are the resources data. You can see just below it, and here you can see, you can give your name, author name, like your name, and you can write some data. See notes also, so that you remember what you have done. Here you can write some notes that this is the demo program or whatever. You can write any story, whatever stories is like, right. So now the point is that I have not feed any data. How this panel will generate? I know the formula, and in that formula I need only one thing, that is radiation, solar radiation. Temperature I am not taking. Let's say if I am taking temperature, consider effect of temperature, I have to give temperature data also on each hour. What is solar radiation, what is temperature, right? In case of wind turbine, what is wind speed, what is whatever height of the everything, right? So in that case, economics, first I will do the economics. Annual real interest rate, this is the interest rate. We all do all calculation with the interest rate. We consider this is a must value, 6%, 8%, whatever the rate is. That is up to your system. Let's say कि your आपका interest rate is in India 8% है, and government has provided you subsidy. So interest rate is, let's say it become 4%, right? So interest rate is up to you, but there will be some interest rate. Without interest rate, we cannot go for financial calculations. If I am investing 1 lakh in 20 years, what is the value of 1 lakh? I have to consider. Without interest rate, there is nothing like financial calculations we can do. Otherwise, life will be so simple. 1 lakh invested and power generated, so simple. Cost of electricity, right? But it's not like that. Every time component, value of money, inflations, project lifetime. See, 25 year I have taken. So what we do, we match the things. See here, project lifetime I have taken 25 year. Solar photovoltaic life I have taken 20 years only, right? Battery life I have taken 4 years, right? Inverter life I have taken 15 years. So I will adjust the things. Let's say I am taking project life 20 years. Now, one thing is clear, there is no replacement for solar photovoltaic panel, right? 5 replacement for battery, because I have fixed the value. 1 replacement for inverter. So I will calculate all this money, that after 4 years this battery's amount is this, inverter and salvage value will have also. Inflation is there. Let's say some fixed cost is there system, which is not included in component cost. Let's say you need to build a platform and you need $10,000 for this, because these all costs we have given is just like component cost. We purchase a solar photovoltaic, we don't include the installation cost in that, right? Suppose I want to put it on my roof, so there will be some, let's say 20,000 rupees I require, right? Labor charges and all that. I purchase from a website. They are not going to store, and I'm going to put a wind turbine or small hydro. Capital cost is required. You need to whatever. Operating cost, system fixed cost. Suppose you want to have 4 worker, 4 labor, right? Their cost is required. Recruitment cost, whatever. Maintenance cost, whatever. Capacity shortage. Let's say penalty. Let's say your load is not met, and you want to put a penalty on the system. Let's say you have a peak load of 55, and sometime your load is not met and 54 is generated. So 1 kilowatt, you want to put a penalty on any. Let's say I want to put a 1,000 penalty. My load doesn't match. So all these issues we can address. If you don't put penalty, it will go freely. So simple. If you put a penalty, that means you are giving him a giving this software a constraint. We have to take care about this also. If something goes wrong in the system, we need to pay a penalty of this much, right? Now the point is, this economics part we can do, right? We can feed whatever. System control, let's say simulation time, step minutes. Let's say ये 120 मैं 2 hours के लिए करता हूँ, but below that it doesn't do that part. Load following, cyclic following, what you want to say, it's up to you how you system you want to give priority to any system. You want to say cycling following load, you want to have multiple generators, you want to have 2 type of wind turbine, these kind of all parameters are there. Temperature I have taken, right? Now the point is how we feed resources. So I just click on solar resources. Now this is again that load kind of thing come up. Yes. Now what I am looking for is how much solar radiation is available at my site. What is solar radiation available? And you know the graph will be increase peak time and it will be decrease. It will be something sinusoidal, half cycle of sinusoidal kind of graph, right? And though there is no solar radiation, like in it will be like a curve, right? So how to find out data first? So there is so many methods to find out data. Again, you can directly find out data from internet. If you are connected to internet, get data via internet, right? So you are supposed to give latitude and longitude of your location, right? Suppose Chandigarh is, you just do one thing, you just select your site, right? And you just find out the coordinate of the site. Very easily you can find out coordinates like Chandigarh. You just type Chandigarh in Wikipedia and you will find coordinates of Chandigarh. That Chandigarh is situated at this longitude, north to south, and very easily you can find the coordinate. So you just feed the coordinates, whatever it may be, 272, whatever exactly coordinate is there, right? Or simply you can find out it from time zone also. Like we are in India, so GMT plus 5. This is any data, right? Any rough number. You want a particular space location data, you just feed the coordinate, right? And if you want any data from any site, some inbuilt data is there in this. See, almost every country's data is there. Central Africa, see all this, Canada and all that, Afghanistan, Pakistan, sub India. See, so you can get the data. One thing. Other thing is you just give it a again manually, right? You have a word file and you want to import your data, and let's say January May I have a 5 kilowatt per meter square per day average solar radiation in my space. In February, let's say again 6, again in March it goes increasing, 8, 9, 10, like July also 10, August a little down, September let's say again down, October 7, 5 and 4, let's say. So this is site specific data. This is clearness index. Clearness index is how sunny day is, right? How clear the day is. So when you are connected to the internet, that is very easy. You just take the data from solar radiation from any site. Even if you go to the NASA site, they will provide you a zip file. In that you just feed the data. They have 10 to 15 year data available with them, and you just give them dates, coordinates also, obviously coordinates and dates, that from July to this year to this year they will give there is some system, right?
So here only 1 year data is required.
1 year. We are going to simulate it for only 1 year.
If we want to simulate it for last, let us say I want to take the data for last 10 years.
No, it will simulate for 1 year.
Only 1 year.
Only 1 year, right? Because in that case you are supposed to give more and more data. Things will be more complicated. Because what we do is, see, the point is when we talk about cost of electricity, first thing, right? We take that how much money we have spent in a year and how much electricity is generated. That is one concept. Suppose you have a different data, 10-year data. So there will be 10 simulations. Every year, according to your data, the cost of electricity will be different. It doesn't do that part. See, you have one data set available with you for 1 year. Cost of electricity will be different, right? Next year, cost of electricity will be different because your resource data is different. Third year, cost of electricity will be different. So there is no limit for that. You can go up to say 50 cost of electricity. There is no provision such like. So it simulates only for 1 year, right? Any year, you just take the data and you just feed the data, and it will give you the cost of electricity, right? And we all do this for one year also. We calculate cost of energy for 1 year. Even within the system, we calculate even for months, but it will do for 1 year. Throughout the year, that will be the charges for electricity, right? So again, scaled annual average, see 6.97, whatever I have given. And here also you can change, suppose 8 is the average, 9 is the average. In these windows, you are giving more and more variable to the system. Suppose data is 11, data is 12, 13, something like that. So more are the windows, more are the system say going to take the time. Now you see. Again, we can do the same exercise also. Suppose you want to use this graph in your paper somewhere. So again, you can copy, and suppose you want to take this data, export data. See, again, you want to plot the data. See. So this will take data from, if I have selected this data GMT plus, this will take the standard data. So again, you can plot this data. You see. Now you see. Right, I have taken a standard data, GMT data, 5.3 India ka data hai. This is for solar radiation, right? This is like January we have less, February. You can see, you can sense it from graph.
For a country, not for a state.
Not from a
They're
state.
asking for a state.
Yeah, not state, for your location where you are sitting.
We are sending the coordinates to them.
Yes, they will give you the data.
Exact coordinates.
Exact
Sending a
coordinate. You just feed the coordinate of this room, and you will got 1 year data from internet. Homer is directly connected to that site, right? They will give you the data. Wind, temperature, solar resources, everything they will give, right? And again, you can do the same thing here also. Here you can export data. See, suppose you want to use this data somewhere in your MATLAB file, let's say. So you need this data. You have taken the data, you have not done anything. Say, suppose I want to take this data in my MATLAB file somewhere. I want to use this data, right? So I will save this data. This is, let's say, PV data. Sorry, radiation data. I can save it again. Now see what happened in this file. See, every time these values are 0, right? Because there is no solar radiation. You can see the curve, na? Increasing, 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 and again see 24-hour curve is there. And here you can see in hour also 1 day data. See, any date. See, you can see. See, this is July 3rd data. Time is 0 to 6. No solar radiation is there, right? It goes up. Yeah. Color is okay. Color I cannot change that.
No, now it's visible.
Okay. Right. See, increasing, and see, max. It goes maximum up to around 12 o'clock, and then again it decreases. Again, you can extract this data again, export data. 1 day data will be there. So you can use that data anywhere in Excel file, in MATLAB file, in any file you can use that data. And just zoom it out and see everything, scale data, baseline data, anything you can see here. This is complete here. Month wise you can see, and here you can see from different issues, say hourly, monthly. See, you can change, you can see DMAP. You can see profile every month's profile, different profiles. You can see PDF function also, histogram kind of thing, CDF also, DC also, everything. These are basically kind of maps, nothing else. Right.
Excuse me, sir.
Yeah.
Sir, sorry to interrupt you. Could you please explain what are D maps?
Sir, DMAPs again, it gives you the, say, complete data on the same scale. Like when we have a hybrid system, right? Right now, what happen is, like I have only solar radiation data, right? Only one component is there. When we have all mixing data on the same platform, so you can extract that data again same by clicking on the same data. So you will got. I will show you later on, right? When we will simulate this part, right? I will show you. Don't worry. We can extract all data. This is data extraction and nothing else, right? So where are we? Yeah, okay. What is this? Yes. Okay. Right. So we can see that all this data is available. These are basically kind of plotting, nothing else. So you can, point is, you can take data and you can plot whatever the kind of, say, let's say you want to use a histogram, let's say, for an example. Histogram, you understand? Right. This is a curve, it is a bar chart, right? And you want to plot it in a, say, line or in a dots, in a something like that. So here is no plotting system. It is a fixed kind of map, right? So let's say you want to plot it in a histogram. How many times in a year, let's say, solar radiation was 10, yeah, 1 or whatever it may be, jo bhi value or whatever the value is. Then how you are going to do that part is, if you have data available with you, you can plot it at it anywhere. That is the best part of this. So you can extract that part, right? So these are all say, and you can find it, you can help it, you can get a help. What is this all say data is all about, right? Right. So these are the basically how we plot the data. Nothing else. This is up to you how you see. You want to see into DMAP, PDF, or whatever the annual scale, whatever the, say, method you want to see, or you want to see data only. Let's say, for an example, you don't want to see any plot. Then you have data, and after you have data, you can plot. You can go to any mathematical presentation of data. That's basically mathematical part, right? Constraint you can give minimum annual shortage, zero. We can minimum renewable fraction. Let's say we have a system where I am putting diesel also, right? And I want that at least 50% of power should be from renewable sources, at least, or I want 100% power should be from renewable. So I can give that fraction. Operating reserve and all this, all power system component. Solar power output, I want 50% at least. Wind power output. These are the all constraints. Again, constraints are there, 50, 20, whatever the constraints you are giving, it is going to be, take it. Saving is there, anything. So now you see, so far we have taken the data. Let's see. I'm going to put some wind turbine also in this, right? Right. Clear? Now there is a wind turbine in this, right? So I'm going to again connect. Again, there are some say inbuilt turbines are there. See here, you can see here, right? Let's say I'm taking generic 1 kilowatt turbine. Now the characteristic of turbine, say again, 1 kilowatt DC. This is a DC turbine, right? Suppose you want to have your own turbine, so you can go for the new. You just give this characteristic curve, wind power output curve, characteristic turbine curve. That turbine curve vary from turbine to turbine. You just feed that curve, and characteristic will be generated. Power will be generated according to the formula only. If power is less, again the mathematical concept will be remain same. Like if how to find out power from a wind turbine, that is formula is there. If power is less than minimum cut-in speed, this is the say wind power. If power lies between cut-in speed to rated speed, this is that goes according to the velocity cube. If power is between rated to say cutout speed, rated power will be generated. If wind speed is greater than cutout speed, no power will be generated, right? So that formula is there. That's how we calculate the. Even mathematically, we can verify the things, right? Suppose how much 1 kilowatt solar photovoltaic panel will generate in a day. If you know the solar radiation, I know the formula, and derating factor I have given 80%, let's say. So GT into 80 into 1 into जो भी solar radiation divide by 1000 watt per meter square, right? So you can even match your power with the you can cross check your power, right? So if you have, like, see, you can give a power curve to this, that 3 pe there is power generated 1, so you can design that part, right? See, this is particular one turbine, this generate in such a way that if this is the power, this is the wind speed, it will generate in this speed, right? So if I'm not using say any new, I'm using inbuilt power, so I'll just select it from here, and AC or DC depends upon me. So again, let's say I'm taking this generic G 1.5, this is 1500 kilowatt AC turbine. So when I clicked on this, say automatically it should go to another side of the system. See, when I click OK, it should be on the AC bus. See, right? Because now I have selected a AC turbine. No converter and say nothing is required in that case, right?
So there will be a separate window for that, just like in zoom and shield.
Nothing.
No, it is just one.
It will be here only, right? Suppose you want to use your system in somewhere, then you can print it. Print means you can go to the print screen and it will be in. You can use that technique only. Suppose you want to cut this system, you want to use this system in your paper or somewhere. Yes,
Yes,
this is screen.
suppose this one.
You want to means use this screen, use this system. You just yes you just go to print.
Actually, I was talking about
No,
in a zoom
nothing.
state.
Nothing.
Just like-
There is nothing
We
like.
have MATLAB in
No,
zoom.
nothing like that. Right?
No systems, no larger systems we are going to integrate over.
No, we can go up to some. See, if I am going to increase the number of say generator, all these value.
Property and
See, yes. See here.
There
See, the size will increase
Okay,
automatically.
automatically.
Automatically, it will increase,
Okay.
but you cannot take it out from the system, right? Like you want to use, so you have to cut that. You have to do that part. There is nothing like you cannot see the system separately, right? So, oh sorry, I was using wind turbine one, right? I'm not using any generator right, so far, right? And I'm not using even battery too. So this was the system. So I have selected one turbine. Let's say I have selected 1 kilowatt DC, or I have selected any another turbine. It is also say new. I have this is 30 kilowatt AC. I have taken see. Few inbuilt turbine are there, right? And see So again, I can have a new turbine. I can give the characteristic and I can have a new turbine. Now the point is, I'm looking for the cost. Let's say this cost me 3,000 per kilowatt. Every cost will be in kilowatt only, right? Suppose let's say operating and maintenance cost is 2 kilowatt. Now you see, suppose I have a cost variation. Something is up to 30 kilowatt, let's say up to 1 kilowatt, the cost is 3,000. If I go for a bigger, up to let's say 5 kilowatt, cost is 3,000. See, and above, if I purchase a turbine from more than 5, the cost, let's say, reduce 6. I can give here automatically. Let's say 6 kilowatt turbine just cost me 16,000. See, right? And replacement cost again 16,000, and operating maintenance whatever I am giving to you. See, hub height again I can change. Suppose I have a turbine hub height of 25. Again I can put sub-sensitive values. Suppose I have a same turbine, same characteristic, but I change the hub height. So basically, what will happen in case of wind turbine? The power is only dependent upon velocity, area, and see velocity of the wind velocity that increase with the respect to height, right? More is the height, more is the wind. If the scale data is let's say 7 meter per second, and that is so what we do is we fix a hub height here, right? 25, and we take that data. We have to match that data also. Suppose you have taken that data, wind speed data at a 50 meter height, and you are taking hub height of let's say 25 meter. So you have to adjust that. So what we do is we keep it simple. It according, and you can find out how they change. See here. See here. All this thing. See here. The wind turbine hub out is height from ground with the rotor seat. Hub height typically in 25 meter. 25 is like that. See, and you want to say change this. These are the total capacity, and see. Yes. Excuse me. जहाँ पे connect किया था. Hello. Hello. Somebody asked me what is DMAP. So you can go to the help file and you can find all the details of DMAP. See.
Yes, sir. Thank you.
Yes. Yeah, you can find out see what exactly DMAP is, right? So a DMAP.
There is a type of remote sharing of our data.
Yes, you just whatever the query. Hello. See, whatever the
Yes,
query you have, you just type here. You will find the answer. How
sure, sir.
See, DMAP.
Okay, sir. Thank you.
Now, see what I was talking about: wind velocity change with height. So how that change? See how we got a distribution site. See, these all formulas are there. This is Weibull distribution is there. See, Rayleigh graph is there. Wind histogram is there. How we calculate? See, function the wind velocity, that is a function of two parameters. Say wind speed, Weibull shape parameter, Weibull scale parameter, Rayleigh function, Weibull function. Every plot on a site we find out. Why we do this? All these things is, suppose let's say if I have a site and then doesn't fall in this graph. Let's say, right? I have a particular wind side and that does not look like the graph of the wind speed with respect to probability. It doesn't look like a Weibull function. It goes up to let's say ramp signal. Let's say this graph at a particular site. So I'm not going to apply that. I'm not going to apply wind system at that particular site. So that should be the shape of the curve should be Weibull function. And most of the time we don't even care about Weibull function. When we take k equals to 2, we talk about Rayleigh functions. So Rayleigh function is one of the best site for the wind turbine wind location. If the graph wind speed meter graph is like in the k, you can see the green one, the third one from above. This is the best location for, say, to install a wind turbine. So that's why we do all this data analysis, right? So again, here we have given so many variable. Okay, lifetime, hub height, everything. How many quantity I have to consider? It's up to me. Let's say I want to keep it up to 6. I don't want to use more than 6 turbine in this system. So I can put a cap. That's up to me. Suppose I don't want, I want maximum. Let's say I want a hybrid system where I will have only one turbine. So limitation is there. See. So here I can give the limitations. Now it will simulate only for one turbine. Suppose you keep your option open. 1, 2, 3, 4, 5, 6, 7. Now it will select from 7. So maximum, every time you have to give the maximum and minimum value. Suppose you don't want to go up to 7, you want to use only one turbine. So simple. So at my final answer, it will be one turbine, right? And again, new, you can find out, you can do so many things. Again, you can go to the help and you can find out whatever the, say, what is the baseline data, what is anemometer height, see, what is autocorrelation factor, what is, say, attitude, what is, say, how the things change, how it calculates, see, everything you can find out. Very even the interesting part is it looks very simple as compared to the books. If you find out any solar photovoltaic or wind turbine book, things will be more complicated. You will see hundreds of equation are there. At the end, which equation, azimuthal angle, and they complicate things. So like you cannot find out what will be my power. But if you go with the hammer, you can find out very easily. There is only 3 equations or 4 equations, say, you can find out, right? Right. So everything is there. See here. Say this is the histogram. See. So everything is there. See. K value. Everything is there. See. Every part of wind turbine, every part of, say, everything is there in this, right? So far what we did is we have connected the system, right? Now if we have every data available with us, we have feed all the data. Now data will take real-time data. Real-time data means in my country, what is the value of 1 kilowatt PV cell? I will take a realistic data first thing, right? That in my country, let's say 1 PV costs 60,000 rupees. So I will convert that 60,000 into dollars, and I will take the real-time data, right? Once you have collected all data, see, I have not taken the temperature data, so it will show you some warnings here. I have not given any temperature. Suppose I give minimum temperature 12, say, in Fab it increase 15, 16, 17, something like that, 18, 20, 25. If I'm not taking temperature into consideration, I will go to PV and I will remove it. That's it. So simple. Because in that equation, I am looking for only solar radiation. I don't care about what is temperature is. The temperature is removed from my equation. Now I'm going to calculate it. So I have just taken the random variable. So you can take actual data and you can go. Now I will calculate this value. So it will start working like this. Now you see what happen is if it gives you some warning, right? So we have to read these warnings first. It says Homer found no feasible solution because the maximum annual capacity shortage constraint. We have just click any value somewhere, right? To fix the problem, it will tell you what to do. Try one or more of the following suggestions. Consider a large PV, right? Consider a large number of wind turbine. Add a generator. consider a large battery bank. Increase the maximum annual capacity sortage on constraint window. So it will tell you ki where you are now. So let's say constraint value will see whatever the he is saying, this software is saying, you go to that part. Let's say PV, we can increase PV. Let's say 100, 200, 300. Again, we run for it. Again, if you don't find any solution, we just give it some feasible values. Again, there is some problem, right? So in such a way, we can give maximum number. We don't have any problem, right? We don't have any problem. We just give a feasible data and see why this thing is happening, because we have a 54 kilowatt peak load. So we have to adjust the thing. So I'm going to increase all this size, and then things will become. So I'm just taking a whatever I have designed one system. I am taking the just because this value I defined them.
Excuse me, sir.
Yeah.
So the PV and the battery bank connected to the DC bus.
Yeah.
Since we haven't connected any converter
Yes.
between the DC bus, so I believe they are floating. That's why we are getting the error.
Yes, absolutely right. So I have converter, add converter. But before we ever did the converter, I have not seen the part. Right? Sorry. Let's see. Yes, we got the data. So it's going to see more is the sensitive analysis, more is the variable I am increasing, more is the time it took. Now you see, can you see it running? Can you see it simulation running? You can see that.
Yes, sir, we can.
Yes. Now you see the sensitive analysis. You see sensitivities. I have given so many sensitivity, randomly sensitivity to this system. That's why it will run up to 126 time, and each simulation will run up to 4104 times. See, so it's going to take more than 1 hour. See, 11, 12, 126. You can see every time it reach up to 4104, and it again repeat for the 13, 14 like that. So I have just given it some randomly sensitivity, so it will show you the results, right? So it will run like 126 times. So I'm going to stop it, right? Now see. So this will run like according to this. Now these are called optimization results. Now suppose I am just taking it. I want to select this, and this will be according to the say CUV. I just randomly stop this value. So I'm just taking one. Already I have built a file, and I'm just going to open that file, right? I am going to take wind plus PV plus battery. Okay, I have just taken one file, right? Result is already calculated. So in this system now you see, I have taken two load. One is domestic load, right? I have given the values. All I have taken another load, that is community load. Two load I can give. I can give even add some deferrable load. Deferrable means whenever there is excess electricity, it can be served or something like that. I can give some heat load, thermal, hydro load. I can give that part, right? I have given this cost analysis, one panel size consider up to 1000. It's up to me. Genetic, I have given some values. So batteries again, I have taken maximum values. Maximum. You can go up to maximum. There is no problem as such. So now you see, I will analyze the results. See. So when we calculate it, so it gives us result in such a way, like these are called optimization results. Now we can see overall also this how much it has taken. See, this is the overall result of obtained from this software. Now how to analyze, how to justify the things, that is the point. Now how to select the system. This Homer, what this do is this select system, and this for this particular load, it has selected a system that is a hybrid system that has 100 kilowatt panel, right? 40 wind turbines, right? No diesel, we have not added any diesel, and 1000 batteries, right? 45 kilowatt ka converter, and the capital initial capital cost is 592 lakh, 5 lakh 95,000 total. Operating cost is this, total NPC is this. Cost of electricity is something $0.518 per kWh. And rest is they see in all increasing systems. See, 0.4. Next combination is this. Here it has selected 100 kilowatt, 140 turbines, 1000 battery, 100 kilowatt converter. The cost increase. So in that way, even that you can find. See, if this system is totally met by wind turbine, here you can see in this result. See, there is no PV involved in this system, right? You can see there only wind turbine, battery, and converter is there. See, no PV is involved in this system, but the cost is 0.775, and there will be some cases where PV and battery will be there. So it's up to how we design the system. Now, how to analyze these things? Now, again, once we got a optimization result, we'll see what we got, how much electricity it has generated, what happened to the battery, what happened to the turbine, right? So we just double click it. And if we have given some sensitivity analysis, it will show up in some window. Here you can plot according to the sensitivity. Let's say I have given a sensitivity of if fuel price increase, what will happen to the cost of the system. So I will, when I will use a diesel generator, I will give a fuel price change. Let's say if I have that file available with me with diesel. Can you find out? Yes. See, right? So in diesel generator, let's say,
We are seeing only one yellow line.
yes, I will plot the generator. I will plot the data. I will plot. See here. I will give the sensitivity first here. Let's say when I put a diesel generator, see, first I will see what is the fuel. Next part is fuel. I'm using diesel, let's say, right? So diesel, I will give you coefficient. This is one equation is there when diesel generator to calculate the power. The load is adjusting. Sorry, the power is adjusting. Power is calculating according to the say fuel input also. So A square B square some equation is there. So according to that we calculate. And we are not supposed to say run on full capacity. Suppose sometime I have a generator of 1 kilowatt and I need 0.5 kilowatt power. So I'm not going to run it 1 kilowatt. I'm going to run it for 0.5 kilowatt. So what will happen in that case? The fuel input will be different, and that is non-linear curve, right? It's not like that ki half rated hai to half time half liter it will consume, something like that. It has some particular equations, right? So if I don't have a larger load, I will run diesel generator according to my system. In that case, every hour, suppose, see, fuel input change, right? Fuel input change, money change, because you are buying that fuel. See, and see, these are all calculator output, fuel consumption. You can have generator size, whatever, and see, there will be some another. Now you see, here in this Homer, you can find out so many uh, fuel input. Let's say biogas. Now it's a biomass generator. It becomes automatically biomass generator. The type of input depends. Say input generator. See, diesel. Instead of diesel, you are using ethanol, methanol, natural gas, whatever the system fuel input you are using. Now you want to say schedule it. Again, there is a facility in this software. Suppose you want to schedule it on, you want to keep it optimized. When it is required, it will run. Suppose you want to force on, let's say. So I want all January, it should be, let's say, on, forced on. See. and I want to it 4 stop. Let's say I don't want to use generator in say January. I have a constraint. I don't want to use generator in December. I don't want to use genuine generator in these 2 months also. I don't want to use say generator on weekdays in April. See, and I want to use it only for 2 hours. Let's say in March. That's it. So now, and I want to use it at a full capacity. Let's say. What will happen in that case if you are going to use it for full capacity? It will run for full capacity, right? So there will be some windows there. You want to use, right? You go to this diesel resource. See, you can change here price. Let's say $0.8 per liter, and you want to see the effect of changing of price. Let's say tomorrow there is $1 per liter. Next day $1.5 per liter. Now, when you will see the optimization result, right? Here you can find out generator some ratio. Yeah, minimum load ratio is 30%. You want to keep it 100%. Say it means it will run on full capacity, whatever the load is. Let's say you have a 50 kilowatt generator, right? And load requirement is 10 kilowatt. So what will happen if you don't consider it minimum load ratio, 30% or whatever the value is? So what will happen now? See what happened in case of generator, the complexity of the system increase, because see life time of generator is operating hours, not years, right? See, generator lifetime is operating hours, 15,000 operating hours. So you are going to make it 4 zone, 15,000 hours. So you want to make it on full year. That's a generator. So within 2 years you need a replacement, because in a year 876 is number of hours. In 2 years it is exceeding from 15,000 hours. So one constraint is that you want to keep it minimum, so that the life of generator become more. See? So in that case you go to that window, and here we can analyze everything. Is the cost of electricity is $0.518 per kWh, and here I can see how much electricity generated. What is see here, this is net present cost. PV this much. So I will take some feasible. Okay, let it be. Replacement cost is there. If I click on the analyzed, say, cost type, analyzed cost type, generally Homer use analyzed, and we want analyzed cost system. Analyzed means what is the expenses for 1 year, when we have calculated everything from capital to end, that we have calculated everything, salvage value, replacement value, what is the annual expenses, maintenance cost, everything we have included. So the manual analyze is this much system, $7636 per year. How much load we have served, that will give you the COE, cost of electricity. So Homer calculate analyzed cost. Analyzed means for 1 year how much we have spent, including everything, including capital, including purchasing of devices, including replacement. You see, here again you can call this data export data. Here you can save this figure. This is again, and you can analyze even more deep by component. See, by cost type. See, capital, replacement, operation. See, you can see the details. See, everything you can see. You can compare in even see this system to this system. You can compare. If you have only wind and you can have this, what are the things which is different except the cost? See, everything you can compare here. Cash flow. Now you see, cash flow is generally people from finance understand that cash flow, how much we are giving and how much per year we are taking, something like that. If we put it on negative side, expenses, and earning we put on upper side on the horizon. See, this is the capital, 6 lakhs is the capital, and these small are say operating and say operating cost, and you see the replacement cost. It happened after 10 years. The battery life in this system, if we have managed SOC and everything, the battery goes up to 10 years. The next battery is replaced by or something another component. By component you can see by cost type, by component, by display, anything you can see here. Discounted rate, everything, every cost say you can see here. Now see the electrical part. Now see, this is electrical part. See, in this system, the primary load is 173,680 kilowatt per hour, right? Total load is 173,680 kWh per year. PV array has generated 367,257 kilowatt hour per year. Wind turbine has generated 622 kilowatt per hour. Generator has generated 821 kilowatt per hour. Total energy we have generated by this system is 368,700, 100%. Now, you see, we have generated 368,700 kilowatt hour per year electricity from this system. But the problem is that we have served only 173,680. So this is the excess electricity which is goes wastage. Suppose you put a deferrable load, you can use that electricity. And we are paying only for 173,680. So the cost of electricity will be annualized cost divided by number of units divided by whatever the money is required. Now, again you can take this data, export data. Again you can find out how much, even see hourly you can plot this data. See, when you go to this window, you can see what happened on a particular day. I will take example of, let's say, first day. What happened to the 1st January? Say, right? So I'm going to make it. First, I'm going to see primary load. This was the load in that system. I have designed this system. So this is the load. Right? Clear? I have taken load. This is different system from the very first system we have started. This is PV power generated. See, can you see this one?
Yes.
PV power generated. This was the load, and this we have generated 2 kilometers, something like. This is turbine generated power, blue one. This is generator 1 power. Generator has not generated anything because it doesn't require. We have enough plenty of. Now you see, load is very small, and PV we have generated a lot.
We are getting only load value.
Yellow is there.
Yellow as well.
Yellow.
Okay, yellow one is
Yes.
Just like this.
Now see. Can you see now? This is the power.
yellow is visible now.
No, but I cannot change the color. See, this is primary load, right? I can make it in 2 window. Now you can see
Okay.
yellow one. This is PV power generated. Now you see this is wind power generated. This is generator power generated. No power is generated by generator.
It's not visible. Okay.
Again, yes. But I cannot change the color. Sorry.
Exactly.
And this is the primary load, sir. We have completed, and this is excess electricity. See. We don't require this electricity right now, but upper portion we don't require. This is excess. If we have a deferrable load, we can give it to the deferrable load. But this is not counted in money because we are paying only for the what we got, what we received, right? So this is excess, we can go to deferable. Now see, unmet load, nothing. We have all load met, right? Inverter power input, inverter output, rectifier input, rectifier power output, battery input. Now you see battery state of charge. See. First we have taken from battery initially when there was no solar photovoltaic, right? We have taken from battery, the black one, right? When power comes up, we are feeding to the battery. See, in next January 3, again it goes down. See. So battery, we are taking from the battery. How much power we are giving to battery? How much we are taking from battery? We can see. See. I just want to consider on battery only. See here. See, match the graphs. In first hour, January, we are taking some power from battery. Below zero, we are taking power from battery. 40 kilowatt power. See, this curve is going down. Again, we are taking power, and again in second hour, see, we are giving to power to the battery. See, again we are taking out from battery, and complete year we can see what happened to the battery. See this one lower, and you see every time the SOC of battery is maintained. See, the state of charge of battery never goes beyond 30 because we have fixed the mark 30, right? See, 20, 40, 60 and 80, 100. It never goes down below 30. So what happened to that 30? Now you see, you just imagine that. What happened? This is approaching towards 30. That means this is a critical situation where battery has low power. So at this time there should be some wind or generator kind of thing. See, so I'm just going to this date, July, where SOC is very less. See here, right? So let's see what happened on that day. So see here. See, generator is all the time silent. See. Right? All the time generator is not working because enough PV and everything is there. See. No need of generator in January, February, March, April, May, June, July, whatever. All of a sudden we required a say generator. And this work only for very few times, very few say systems. See here, because state of battery is not okay. Yes, negative is, and power required is say load is always there. See, this is a load. So here we required a generator. And if we don't have this generator, we have to increase the size of battery bank so that it doesn't go below 30%. So system will be changed. Suppose I remove diesel generator from this, everything will be changed. And again, you can analyze this data and you can enjoy with this data. See, whatever again the same concept is there. Whatever maps you are going to put, you are going to use this data in your MATLAB programming or somewhere, whatever. See, and this look again. See, anything you can export again this data. See results. I am going to export this. See, again you will have a Word file where you have all the data with you. See, where I have stored. Export data. Sorry. Now you see. Now you see. You have complete data for 1 year. See, you can analyze from here. 1 hour primary load is something 35. You can see primary load PV power 0. No power is available. At 6 o'clock, there is a little power available. This is inverter output, power from battery. You can see from, say, above, what are these parameters? Battery state of charge. Now you see the battery state of charge. You can see from here the battery state of charge is 90% right now, and we are taking from battery 39. This much of power we are taking from battery. So battery state of charge will go down, right? See, and minus 44 is required, and we have enough, so we can do that part. We can go, and there will be some time. See, when it goes 30, 30 somewhere in July. See here. 30.33 is the state of charge, and you required minus 29 kilowatt power from itna value. So battery cannot give you, because you have put a constraint of 30 kilowatt. Some another. Now you see generator will be there somewhere. See the 6.49 is from generator, right? So I will take one grid connected example also. Let's see what it says. I will take. um, Yes, I've taken it. I've designed this biomass with grid, hybrid PV system, right? So again, when you connect to the system to the grid, you are supposed to feed the electricity price and all that part. See here, I can feed price sell dollar per kWh 0.1 sell back demand whatever, and normally it's like that in some state, like when you give power to grid, they charge a different rate, and you take power, they charge different rate. And if you are providing to the grid, almost in some state they will,
Larger.
yes,
They provide very larger.
very large amount. No. When you give to them, they charge you at a high rate, and when you take, you are normal customer. Yes, like if unit is 5.5 rupees, that is for everyone. If you are selling to the grid, they will take you from like something 7 or 8 rupees like that, right? So again, you can have sensitivity here. You can take even real time prices. You can import price data
That
per
can
hour.
happen.
Yes, stock market, you can do that part also. Every time, what is particular hour, what is data, you can do that part. Emissions, you can see, you can control, and you can see if you are using generator, how much CO2 is emitted to the atmosphere. You have used the generator, so how much you have emitted sulfur dioxide, everything you can see from this software, right? Advanced C, interconnection charges, standby charges, sale capacity. Now you see that we have a limit on selling. Because why we have need limit of selling? Because every time what we are generating is something like if we have AC DC system, we have a problem. Because you suppose you are generating power from PV, right? So you need to sell to the grid, and grid is AC, right? So every time you need to put a converter. So convert, if you are putting a cap on converter, so that means converter is going to convert that much of amount. So there will be one issue. So this, let's say I can sell capacity. I can sell 100 kilowatt only. Maximum value is 100 kilowatt. In that means I should have a converter more than 100 kilowatt. I have to feed the load also, plus I have to sell grid also. Purchase capacity. We can go in a dual way. I can purchase up to 10. I want to keep. I want to design a system where I want to purchase minimum power from the grid, and I want to feed maximum power to the grid, and still I want to have benefits. So I have designed this system, see, in such a way, and you see the results, overall results, and the cost of electricity, that is something like $0.417 per kWh, still costly.
Yeah, there are so many optimized values.
Yes,
that you-
optimization, and they are sorted out according to the COE. See, sometime what happen is few parameters is changed. Let's say uh, some other values are there in this 190 PV he is taking, and 42, something will be there, like renewable fraction is there, biomass ton is, everything will be
Cost
there.
per watt, that is what we are required to see.
Yes.
Our constraint is
Our constraint is
our objective is minimum.
minimum, right? Obviously. So this is according to, let's say, if you are not using PV, so it will show you the result that only you biomass and PV, and if you are not connected to the grid, you can have this COE. So feasibility, we have to check. It is feasible or not feasible. Let's say this system is something 0.417 rupees it gives me, right? 0.47 rupees is too much number. Let's say 60 rupees dollar is there. Still 24 is the cost that is coming to me. So I have to check this system will be feasible or not. And I have, let's say, if I apply some subsidy and I reduce the cost of every component by half, let's say. Suppose I have designed this system and government give me subsidy. Okay, just reduce the price, every component price half at half rate, right? Now the cost will be obviously point two something, $10, and $10, 10 rupees is a very good number as compared to I'm generating my own system. And again, I can check how much electricity I am feeding to the grid. See, I am just purchasing. See, this system is very good. I am just purchasing 13678 from grid, and see how much I am selling to the grid. 275,146 kWh per year I am selling to the grid. So this is a very good system. In fact, cost of electricity is, so what this 27516 kilowatt per hour they are receiving from nowhere. Cost is not a factor. They are receiving this much of power from all kind of renewable energy sources. No pollution is there, nothing like system is there. If you are going to generate this much of power from diesel, now you can compare it. If you are going to, yes, how many pollutant emissions will be there, right? So again, you can find out all how much time this generator runs, how many times it we have to start this generator, right? What is operation life, what is capacity factor, what is cost, what is electricity production, what is output, everything, every data you can find out. And you want to have a plot, you can, again, the export data is every time there. See, converter, in input output, everything, and you can say grid. See, net, see, in month of July, I have purchased 1914 kilowatt energy from grid. I have sold 20,000 kilowatt energy to the grid. Net purchase minus हो गया. Peak demand, energy charges 0. Energy charge minus 2. That means I am earning from, say, grid, right? So this will be somewhere when I see the calculations. So this will be showing my income. See, negative side. The only thing in this system is negative when system is connected to the grid. Otherwise, everything is positive. Yes, we have expenses only. The only income which I have generated is, see, from grid only by selling the electricity, right? So there are so many, and the best part is, just I want to come to the my PPT slide. Then this software has a very, say, wide range of applications. I have just shown you the 3 or 4 data. Like I have taken wind, solar, and say biomass. And you can go for small hydro, you can go for fuel cell, you can go for diesel, you can go for flywheel, battery storage. So many variabilities there. And in last, I am telling you, in 10 years, almost more than hundreds publication I have seen where people are using. I will show you one publication. See, few publication I just want to share with you where people are using these software only, and they are getting very good publications. See, and but the only way is how they are presenting the material. See how, so sorry. You can find out all these paper are from Homer only. I just want to share any single paper. Can you see any application of Homer kind of thing? Now you see. Can you see? Yes. Say this is latest 2014 publication, almost 1 year back. Off-grid electricity generation with renewable energy technology in India and application of Homer. Just simply one application. And best part is there is no cross check of your results. These are not standard results. Simulated result. No cross check is there. So you are the only owner of C. Now you see this figure looks similar to you. And this is not a very good reputed journal in energy. See, he has taken hydro, PV, wind turbine, battery converter, and biodiesel generator. See here. See all. Even he has not done the. He has taken the same graphs by clicking just simply bitmap. See all these data is he has taken. See all this. This is nothing. No, just right click and take this picture only and nothing else. Once you feed the data and you have to just write the things. See all these data is available. Any another paper you can see. Anywhere see every time you can, and you can analyze so many applications. See, once you have a data with you, you can go for solar, you can go for wind, you can compare them, you can add one part in them, and see you can see see now these graphs look familiar to you. See, every time these people are doing the same job. See, and they are very all paper in very good reputed journals elsewhere or something like say. See all data is there. Homework is there. See all. They are just comparing that if you put a grid in this system, if you put this system, all these graphs now looks familiar to you. See, there are so many. Even I am saying there are hundreds publication on this Homer. And nowadays people are doing. They are say what I do is suppose I have a system, right? So in this, I don't know how Homer has optimized the systems, right? So what I do in my research is I mathematically prove that part. Suppose I generated power from PV according to that formula, and yeah, mathematical modeling, right? And there you can apply some say kind of techniques, and you will always find that this Homer is nowhere with respect to techniques, because in techniques you know what you are doing. In Homer we don't know what we are doing. Once you have feed the data, you are free. You just click simulate and that will give you a result. So you can find out, see if you are interested, you can see one of the paper I recently published. Yeah, this one is there. Now this is optimal sizing of grid integrated hybrid PV biomass energy system using artificial colonial. In this, what I did is I take a reference with Homer and I applied this technique, artificial colonial, and I have taken the system PV biomass. So this is a limitless opportunity. You can add like say PV biomass wind. New concept is there, so you can model that part, right? So people are doing like that. See, grid integrated photovoltaic energy system. Yeah, photovoltaic energy system, battery and grid. So opportunity permutation and commutation is see application to Homer. Though not supposed to say converted the things. I think thank you very much. And if you have any query, any doubt, please, I will try to solve. Yeah, please. Thank you. Any questions? Yeah, from your side. And you can download it very easily. Right?
Hello.
Yes, sir.
Sir, I want to. Uh, I am from MMU Milana.
Yes, sir.
I want to ask a little question that
Yes.
is it possible to have the dynamic response of the system, particularly in the term of current and the voltage?
No, sir. I mentioned this thing in starting only. We don't have power system components involved in Homer. We don't know what exactly. Yeah, so we here in this drawback with this system is, sir, that we don't know what exactly going on. Exactly going. We only talk about power and KWS. Nothing else we talk about.
Because
We,
uh, uh, because you have
we can,
shown a lot.
yeah, we cannot see, sir, dynamic response. There is no such concept like P, Q, what is harmonics, what is current, what is voltage, nothing like, sir.
Okay, it's just the economic investigation of the
Yeah,
system.
yeah, that is totally different domain. If you want to go in that part, you have to go for the Simulink system. You need to Simulink a model of wind turbine, then you can see what is P, what is Q, what is current, what is voltage, everything. There you can see. But here, this is more economic aspect software. We talk about money here, not power system qualities here. We don't even know that the system we design is okay or not, because we design on the basis of previous data. What will happen if suppose next 4 month, like one complete month, there is no resources available, no solar, no wind, nothing. So
And
my system is totally failure.
and one thing what I have observed in the various results
Yeah.
that in India we are more concerned with the rupee, not with the dollar sign.
But it
So
doesn't have a option for dollar. So what most of the research do, they calculate the money from money in form of dollar, and then they multiply it with rupees, and they write result in rupees. I can show you one paper if you want. See,
sure.
see here. This is from Swarm and Evolutionary Computational. They have applied a BVO algorithm from India side only, and they are talking about Homer and everything, but they have considered rupees in, say, money in rupees. PV capital cost 2000 rupees per kilowatt, and all these calculation they have done in rupees. So they have converted, they have feed data to Homer in dollars, and again they by using the current rate, they will mention somewhere that $1 equals to
So
something.
manually we have to calculate the equivalent value in the rupee, na?
Yeah, definitely, definitely. There is no provision for rupees, euro, something like that, because this is designed by USA. So only things it understand is dollar, nothing else. Thank you.
Okay, thank you.